Yep. The first speaker is Jan Yuan.
Good morning.
Good morning, everybody. Welcome to the second day of the blah blah blah. Come on, Adrián.
Well, pues the first speaker is Jan Yuan, and he is going to present observing the AT field with 250. Oh.
Okay, so I start. Okay. Good morning, everyone. First of all, very sorry that I cannot attend the meeting in person. So my name is Yang Huang from University of Chinese Academy of Science. And thank you giving me this opportunity to present our proposal for using JST250 survey for ET field to joint search for the first Earth 2. And this proposal actually have a lot of effort from the collaborators, including Raphael from IAA and my student Bowen. John, I think he is also in the Zoom, and he did a lot of work. And also Jienge he is the PI of the Earth 2 mission, and also a lot of members in the ET target selection group. So first, I will introduce what is the Earth 2 ET mission. So in 2024, China have launched the so-called China Space Orange Exploration Program. In the coming 5 years, there are 4 projects are granted, including the ET is one of the first funded project, and it is expected to launch in 2028 to the L2 orbit. And ET is actually the first main part is 628 30-meter telescope, and to see the same regions simultaneously, and they will give the field of view is 550 square degree, 5 times of the Kepler field. This survey will also toward the Kepler pointings, including the Kepler regions inside the field. And roughly, we will continuously monitor over 3 million FGKM type main sequence stars for 4 years. In addition to this main part, here you can see one 35 centimeter micro lensing telescope toward the barge regions. The field of view is 4 square degree, and it's want to search the planet using the micro lensing technique. And for the full details, you can see you can see the girl's paper in archive. And the core science is, of course, obviously, the first is exoplanet, to find as many exoplanets as possible, and particularly want to find the Earth-like planet. And in addition to the exoplanet, also because they have the continuous light curve, we can do the seismology. And so it's very important, also important for stellar physics and galactic evolution. And because for the image, we can download all frame, so we can do stack. So that also very useful for time domain sensor down to, for example, 21 magnitude. So this is the 3 main science. And now the ET science team have attracted over 400 scientists from over 19 institutes worldwide, include at least 4 Spanish institutes I know. And the key advantage of ET, particularly compared to Kepler, I just mentioned that the field of view is 5 times larger than Kepler. So that gives you 20 more search ability. And also another technical advantage is ET will adopt the extremely low readout noise detectors. The readout noise is about 4 electron. And as a comparison, Kepler's readout noise is 86. So that means Kepler, even though the field aperture size of the ET is smaller than Kepler, but the performance of the photometric position is even better than Kepler. In the bright region is comparable, but the faint range, due to the extremely low readout noise, it can be improved a lot. And so that's these two abilities will give the ET potential to find Earth-2 here. There is no planet current found in these regions. And here is some simulations that the team simulated a transit from a hosting star about 16.5 magnitude with a position 34 ppm. You can see the Earth-like transit dips clearly. And to prompt these missions, the ET target selection is very important. So the mission established the target selection group. So I'm the chair of this group and in charge of the ET field determination. So the pointing of this field. So now it's done. And also the input catalog. This is why I propose J plus and J pass to observe this area. And also some other three co-chairs in charge of, for example, stellar activity and interesting object selections. So this is now show you the ET field compared to other planet searching missions. Here you can see just above the galactic plane and to avoid the high reddening regions and including the entire Kepler field inside this region. That means we can have a continuous light curve combine Kepler and ET in the future. And give you a more chance to find, for example, long period planet or other signals from the variable or something. And here is a zoom in of this field. You can see details. Here is the galactic plane. Here's the Vega, and this is how these areas in the sky. And for transit and stellar physics, we mainly focus on the bright stars brighter than 18 because we want very good light curves. So in this field, the bright star brighter than 18 is about the 6 million stars there. And for time domain, they may more focus on the faint regions. This is about 27 million faint target here. For the transit for the bright target star, especially for to want to find the Earth-2, we must first identify solar-like star or solar twins. So that means we need to comprehensive stellar parameter estimates, including to determine the stellar atmospheric parameter, including temperature, surface gravity, and metallicity. And also we want to know the evolutionary stage. About that, it means we want to know the stellar age. And even more, we want to determine the element abundance ratios, for example, alpha abundance, carbon abundance. This information is also wide for ET, stellar, and galactic archaeology science. And in addition to these parameters, we also want the whole star stellar radii is also very important because that determines the transit signal dips. And for the time domain science, we need classification. For example, this faint target are star or galaxies. If it is galaxies, what is the redshift? And this is a star forming emission line, have emission lines or not. This we need to know. All these things properties we need spectroscopy or multi-field survey of this area. There are some existing surveys of this ET area because we toward the Kepler, so some surveys have observed the Kepler field intensively. For example, LAMOST and Apogee, and fortunately, some footprint also cover the larger ET area. And also DAISY give this age observations. And this is SDS5 both observations. But if we just get some, but we add them this all spectroscopic number together, just 0.3 meaning spectra. So this compared to this number is very, very small, right? So another way is the Gaia XP, that is also a low resolution spectral, can also be used to make a classification of target, determine the parameters. But if we require very good quality Gaia XP spectra in this region, is about 1.6 meaning spectral. So it's still not enough. So if we plot this the magnitude distribution of all the star in this area with pan-star detections, you can see here this blue histogram, and this green is Gaia XP. This orange is combine all spectroscopic surveys. So you will see that in here, when fainter than 15 or 16, there are huge gap to be filled. So for the bright target, it's just about 1.6 million star target are observed with SED or spectroscopic information. For the faint, it's just a few, 0.1 million. So that means most of them are not without the low resolution spectral or multi-field SED information. So this is why I asked for JST250 to observe these regions. So before JST250, I tried to design a JST18 survey of this ET field early this year. So we designed a very cheap method to cover all the area with 3 blue band, U and these 2 bands together, because these are very sensitive to the matte lines. So according to our previous experience, with this 3 band, we can determine the stellar parameters, particularly the metallicity. So in totally, because the JPLUS has observed this ET area about 1/3. So we just need to observe the remaining 2/3. So about 40 hours, we can cover all the areas. In that, using these 3 filters, and we can determine the stellar parameter, in particular metallicity, down to 18. So this is the most conservative approach. But this just gives us the metallicity. We cannot know very well the temperature. We cannot know very well the abundance ratio, and we don't know whether star have emission line or not. So even for the bright targets, we need a more narrow band, and for the faint between 18 to 21, so the J plus is hard to give very good SED information. So JST250 is very good for doing this. So for the narrow band, the field try is from T1 to T4. But to save time, we don't need a T4 now, because as someone may know, the Flare X now released the all sky data. So it covered the red regions from 0.8 to 5 micron. So that can be replaced. T4 can be replaced by the Flare X data. But for the blue and green regions, we need T1, T2, T3 filters. So in total, we designed more than 3,000 observation block with some extending the boundary to allowing that finally, if ET points have some errors, so we still can cover their entire regions. So for the three field trials, so in total we have nearly 10,000 observations. The total time.
Hey, Jan, can you hear us? I think he went offline. Let's wait a bit for him to recover. Hi, Jan.
Signal lost. I shall.
Don't worry. Try sharing screen.
Okay. Wait a minute.
Perfect. Go ahead.
Mm. Okay. So now clear, right?
Yep.
Hello? Yeah, okay. I continue. Sorry. So in total, we need 560 hours. So here is the time budget for different tree and the different observation conditions. So this design is to keep each field narrowband have signal to noise ratio greater than 5 at 21 magnitude. Here is the according to the exposure time calculator, we do this calculations. So here the exposure strategy is same as the main service. We do for teaser, and the gain and the binning is also similar to main service. So this is dark time for T1 and T3 is for blue and very red, and the gray time for T2 and T3, and for bright time is just for T2 because the throughput is higher here. So this is the design of the survey. So also we have lots of existing expertise and experience for J+ and JPass that is very helpful for us to push this survey successfully. So I'm also the former member of JPass and J+, and also an extended member of S+. So here I show you two leading papers, first also by me for J+ parameter and S+ parameter estimate. So we're using the J+ and S+ narrowband filters to derive the metallicity down to -4 and the typical position is better than 0.1 to 0.2 dex. And also we derive very good carbon abundance. You can see here the carbon photometric carbon abundance compared to spectroscopy. So this consistency is very good. So we can even to select the so-called some carbon enhanced carbon enhanced stars. So this we have lots of such experience. So when the data is arrived to us, we can do very good in stellar parameter estimate, stellar classifications. And also if we need the data reduction, we also do help for database. For example, yesterday, Hacker's presentation mentioned that our work, I'm very happy that now the JPass adopt our database as flex calibration flex calibrations. So this database is constructed and maintained by my group. The first also is my postdoc. So we released all the JPass filter data here. So if in future, if want any revisions or any specific requirements, we can do that very quickly. And finally is some discussion and summary. So the discussions is yesterday I just checked the footprint of the main survey of JPass. We found that actually the ET area actually 20% are covered by main survey. If the main survey can in advance of these regions, we can save 20% time that can be saved, right, before 2028, because we want the input catalog before the launch of the mission. So if the main survey look this before that will be helpful. We can save this time, reduce from the proposed 560 hours to 450 hours. I just discussed whether this is possible. And finally, I stop here. I think this is a unique opportunity for both JPass and AT. So this about 550 hours is a modest investment. So, but the time is not that large, but it could enable a legacy survey for the ET and the broad astronomical community. So by collecting this data, we can forming a very good input catalog like KIC, TIC. This will be useful for all the community, and also this catalog could very high impact in many fields, not only the stellar physics but also the galactic archaeology and also the exponential science and the time domain. And finally, I think this is a very good chance for JPass as a key partner of the ET to join to search for the Earth 2. And finally, I stop here. So I think together discover Earth 2 for ET and JST250 is a very good good opportunity. Glacio, thank you. Hello?
Okay, John. Anyone have a question?
Yeah, couple questions. Yeah, can you hear me?
Yeah.
All right. Okay. Well, so you are going to observe Kepler these test fields for exoplanets. Are you also interested in exploring asteroseismology to get the stellar ages?
So pardon, I'm not that clear.
Can you hear me better now?
Yeah.
Right. Okay. So all right. So you are going. You want your targets are in the Kepler and test fields.
Yeah.
Are you also planning to explore asteroseismology to explore stellar ages?
Yes, this is also important. As mentioned, is also very important for ET science, right? So stellar physics, seismology. So for the Kepler field, we have maybe more than 10,000 RGB stars. We now can very good seismology signal. So that can be used as an input catalog to improve the age information. But in the future, after collection of the ET, we have more data together, and also that need the input catalog to combine the seismology information together to derive a value additive catalog of the RGB or main sequence age, right?
Good. Thanks.
Anyone next would like?
Hello. Thanks a lot for the presentation. I have just a question about. I saw what you plan what you propose to observe the exposure times. I noticed that you choose 30 seconds per exposure. I'm just curious about the reason. Well, what's the reason behind it? It's because my question is why not 30 instead of 30? Is because you are trying to avoid saturation, or that's my question about the exposure time per individual image. Can you expand a little bit? Yeah.
So you mean why choose half minute, right? Individual exposure.
Yeah.
Hello?
I'm just wondering.
Yeah.
There may be a reason, but why not 60 seconds, for instance? You are focusing on the bright side of your sample. You are trying to avoid saturation for bright stars.
So here, 30 half-minute individual exposure. So first of all, I want to keep the same strategy for this dessert. And second, so half-minute, so that the bright saturation, it could be extended to very bright stars. So we can start. We have a much larger dynamic range from, for example, 10 to 21. If we individual exposure is 1 minute, so the bright end will be, for example, 11 or 12. So this can help first to keep the same strategy to keep to allow the official pipeline to redact our data smoothly. Second, the half-minute can help us a larger dynamic region in the magnitude. So this is our design.
Understood. Thank you.
Pardon?
So thank you.
I have a few comments if it's possible. Is it possible? Hola.
Yeah, Rafa?
Yeah. So I have just a few comments from Jan's presentation. I would like to say that this project, it is really the beginning of a bilateral partnership between China and Spain to use the Spanish observatories to support the AT mission. This part of Havalambre could play a very important role on precursor science that can be done now before launch and that will be used during the mission with the input catalog. I mean, the input catalog of Kepler and TESS, those are papers with more than 1,000 citations each. So this is really relevant for a very broad community. But there are now conversations between CSIC and Chinese Academy of Science to do a bilateral agreement to use the rest of the Spanish observatories to do the ground-based follow-up segment of the mission itself when the mission flies to confirm the transit candidates. So there is going to be an effort to do multicolor photometry, to do low-resolution spectroscopy and high-resolution spectroscopy, precise radial velocities, to do follow-up of the transit discovery. So this is really kind of the first step in which the rest of the observatories, the Roque de los Muchachos and Calar Alto mainly, are going to be supporting the mission, and we are really establishing all those relationships now. And yeah, I just wanted to say that this forms, it is part of a larger project. This is not this is just the beginning of all these preparations in support of the mission.
And this is the beginning of beautiful friendship.
Thanks, first comment.
Okay, thanks very much.
By the way, Rafa, congratulations for your prize.
Thank you. You can see me, nothing has changed. I'm in my pajamas now.
Next speaker is Yantao Li. He is going to present Cosmic Noon survey.
Okay, yeah, can you?
Okay,
Oh,
so yeah, can people see my screen?
Yeah,
yeah.
you can go full screen.
Okay, great. So, hi everyone, I'm Jiangtao Li from the Purple Mountain Observatory, and many thanks for giving me the opportunity to introduce the J-ECOS program, which stands for the JST250 JPCAM EDFN Cosmic Noon Survey, and EDFN here stands for the Euclid Deep Field North. So you see the collaborators including many Chinese people and also Renato Dubke from the JPAS group. Okay, so this J-ECOS program is a multi-instrument synergy program, and today I will mostly focus on the narrowband imaging part taken with JPCAM. Here is the outline. First, a brief scientific background introduction, and then I will introduce the survey design, followed by the photometric survey, mostly related to the JPCAM observation. And then I will very briefly, very quickly go over the spectroscopic survey. And finally, there is a summary in the prospects. The science background of the major science goal of the J-ECOS program focus on the galactic ecosystems, which includes galaxies, AGN, and multi-phase circumgalactic and intergalactic medium, plus some large-scale structures, including galaxy clusters and cosmic webs. So to study the gaseous structures of the galactic ecosystems, there are mainly three basic methods. The first method is using absorption lines, as shown. I think people can. Could you see my mouse? Probably not. But
No.
but that's fine. Okay, that's fine. So the first method to study the gas is using absorption lines from a background galaxy or quasar, and then when the light passes through the intervening gas structures, they will produce some strong absorption lines, and then we can use these absorption lines to probe any intervening gas. And the gas can also be studied with emission lines using either narrowband imaging of some strong emission lines or the spatially resolved spectroscopy observation with IFU. So these are the three basic methods. And so this page compares the existing photometric and spectroscopic surveys. The upper figure and the table shows the major photometric surveys, and the lower figure and the table shows the major spectroscopic surveys. We can see that they are still very rare narrowband imaging surveys, and the JPAS indeed provides one of the first large area narrowband imaging survey with some continuous narrowband filters. So why this kind of narrowband imaging survey is critical in the study of gaseous structures? So they are useful mainly in two ways. The first way is we can use narrowband imaging to directly detect the extended gas distributions, especially the CGM around the starburst galaxies. The upper right figure shows you the properties of the brightest Lima alpha blobs already detected at high redshift. The x-axis shows you the redshift, while the y-axis shows you the Lima alpha luminosity of the Lima alpha blobs. The size of the circles is proportional to the size of the Lima alpha blobs, and the curves shows you the JPAS detection limit for point-like sources. You can see that it seems JPAS is already good enough to detect most of these bright Lima alpha blobs, but this is indeed very difficult because the detection limit shown here is for the point-like sources. And most of these Lima alpha blobs appears to be extended sources even at high Z. And the blobs shown here are the brightest ones we know from the literature. So if you want to detect the fainter ones, you probably need a stacking of the narrowband images of many selected galaxy samples. The narrowband imaging is also important to select the background sources for IGM tomography. The lower right panel shows you the basic concept of IGM tomography, especially using Lima alpha forest. So there are a lot of background, especially galaxies. So we'll take a spectrum of them, and we can see absorption features from the intervening gas. So here, the narrowband imaging is critical because it helps us to select the background sources. So we need the high accuracy photometric redshift to accurately select the background sources for follow-up spectroscopy observations. Okay, according to the survey design, the J-ECOS program focuses on the cosmic node. So this corresponds to a redshift range of about from 1 to 1.4. So this is mostly for two things. For the narrowband imaging, so this is for our selected filters, it will cover some strong emission lines. Well, for our spectroscopy observation, this is to ensure the Lima alpha forest can be covered by our spectrograph. So I will introduce more details about the redshift later. So for field selection, we choose the Euclid deep field north. So this is not only because Euclid has very deep, this is a Euclid deep field, so it has very good archival Euclid data and also quite a lot of multi-wavelength data, but also because we have a few approved synergy programs. This includes the Chinese Space Station Survey Telescope, CSST. There's a deep survey covering the EDFN, and also includes the a 4.4-meter Jiao Tong University spectroscopy telescope, just a follow-up spectroscopy observation. So if you don't know this just a telescope, you can regard it as very similar as a DESI program. So both are 4-meter telescope and multi-object fiber spectrograph. In fact, JUST even has higher fiber density than DESI, slightly higher. So we write a paper justifying this synergy program on the study of the gated structures, and this paper has recently been published in RIA. Okay, the major scientific goals of J-ECOS is threefold. The first scientific goal is to study the galaxies and using the identified galaxy over density to trace large-scale galaxy structures. And in this case, the narrowband imaging will be critical to help us to accurately measure the photometric redshift. And the second goal is to study the CGM. So this is mostly based on the stacking narrowband images to search for the extended emissions around some selected galaxy samples. Well, the third goal is IGM. So this is more or less unrelated to today's talk because this is mostly based on spectroscopy observations. Using the absorption lines in the background, the quasar or galaxy spectra to study the foreground CGM or IGM. Okay, the photometric survey program is closely related to the JP-CHEM observations. The upper left panel shows you the best fit SED using a starburst galaxy model to the photometric data from CSST and Euclid. So you see the blue data points are the CSST covering the bluer band, while the orange data points are from Euclid covering the redder band. They overlap with each other at about 8,000 angstrom. So combining the two, you see that this 8,000 angstrom is at our redshift of interest around the redshift about 1.2. They cover the oxygen 2 emission line and also the Baum break. So this is the strongest feature we want to trace. So combining these two data sets has significantly increased the photo Z accuracy. Well, the upper right figure shows you what has been even better improved by adding the narrowband imaging data from here. I showed JPass, but it is indeed the JP-CHEM narrowband imaging observations, the green data points. So you see the narrowband filters has continuously covered the Baum break and also the oxygen 2 line in a redshift range of from 1 to 1.4. So these two figures shows you the quantitatively how the photo Z has been improved. So the solid curves are the photo Z accuracy by adding the narrowband imaging from JP-CHEM, while the dashed curves are the narrowband imaging only including the CSST and Euclid data. We see from the left panel, this is for redshift about 1.2. The adding the narrowband imaging has significantly improved the photo Z accuracy over all the brightness of the object. So it is at least 2 orders of magnitude improved by the redshift photo Z accuracy. Well, for a redshift at about 2, the red panel, we see this improvement is not significant. This is because features moves out of the narrowband, the wavelength range covered by the narrowband filters. And we also need a large enough sample to do the follow-up, either identification of large-scale structures or stacking to search for the extended CGM. So we use the galaxy luminosity function and the AGN luminosity function scaled to the Euclid deep field noise to estimate the required detection limit. And we conclude that we need a detection limit about 23.5 to 24 magnitude to detect more than 10 to 5 galaxies within the Euclid deep field noise and at a redshift higher than 1. Okay, so this page shows you the results on the stacking to search for the extended line emissions from the CGM. The lower figure just shows you the expected oxygen 2 luminosity at different star formation rate and stellar mass. The green solid line is the star formation main sequence, so most of the galaxies should be around it. The upper two panels shows you the stacking result. Shows you the result for searching for the extended CGM, while the upper left shows you the result for individual galaxies. The solid curve The solid line in the upper left panel is the surface brightness, while the dashed curve is the detection signal-to-noise ratio. We can see that even for the most active star-forming galaxies, with star formation rate about 100 solar mass per year. So over the radial range of the CGM, this is still the detection signal-to-noise ratio is still far below 1. So this means it will be very difficult to detect the CGM around individual galaxies unless it's very active with star forming. Well, the upper red panel shows you how many galaxies are needed for stacking to reach a signal-to-noise ratio about 3. In this case, we can see that for the most active star-forming galaxies, for example, for those with star formation rate about 100 solar mass per year, the magenta curve in the lowest. So we need about a few hundred galaxies for stacking to detect the extended emission at a radius about 100 kiloparsec. And if you want to detect the CGM at a smaller radii, for example, around 50 kiloparsec, we need just need a few tens of galaxies. And even for the less active star-forming galaxies with a star formation rate of about 10 solar mass per year, so we only need a few times 10 to 4 galaxies to stacking to detect the extended CGM. So this is indeed quite feasible for our sample size of about 10 to 5 galaxies. For the spectroscopic survey, I will be quite quick. So because this is not related to the proposed imaging observation here. So there are basically two sets of spectroscopic data, the CSST slitless spectra and also the just fiber spectra. So the CSST spectra will be mostly used for IGM tomography, mainly where the Lima alpha forest. So the left panel shows you a simulated CSST spectra at redshift about 1 point something. This is a background galaxy. So the background galaxy redshift is 1.7, while the absorber is typically in the redshift range from 1 to 1.4. So we can see significant composition draft created by the Lima alpha forest absorption. The red panels shows you the simulated 3D IGM distribution with field of view tailored to the EDFN, the Euclid diffuse noise, while the two figures shows you the different slices. The lower right panel shows you the distribution of background galaxies. So these are galaxies we assume to be redshift higher than 1.5, and there are in total more than 5,000 galaxies in our catalog. So we will take a spectra of every one of these more than 5,000 galaxies with the CSST, and then use the Lima alpha forest spectra to probe the foreground gas. Well, this is the result of the reconstructed gas distribution. The left panel shows you the result of the column density, while the right panel shows you the residual. Okay, so the second data set of the spectroscopic survey is just fiber spectra. So this is mostly used for stacking analysis to detect the metal absorbers from the IGM. This page simply shows you for direct stacking, if we don't know the redshift of the object, we measure the redshift of the absorber using the CSST spectra. Then the stacking, because the spectral resolution is very low, the stacking will smear the signal and we cannot detect anything. But if we know the accurate redshift of the absorber by some method, so when stacking, that's the blue curve here, we can still see a weak signal. Well, this figure shows you another method for stacking using the two-point correlation function method. And the conclusion is it is impossible for IGM, but doable for CGM to detect the metal lines. Okay, so I will be very, don't take too much time introducing the spectroscopic survey here. Okay, so finally, the summary and the prospects. The JX program has a few scientific goals. The first one is to construct a Euclid CSST and JPCAM photometric catalog of the galaxies and AGN and cosmic noon. So here, the JPCAM narrowband data will be critical in improving the photometric redshift and also in measuring the galaxy properties. Well, we will also stack the narrowband images, especially those covering the oxygen 2 lines, to search for the CGM emission in the same redshift range. And also the for the spectroscopic survey, the CSST slitless spectra will be used to reconstruct the IgM distribution using Lambda alpha tomography, while the just spectra will mostly be used for stacking analysis to search for the metal absorbers. The CSST will be launched in 2027, so this is indeed quite firm because this is one of the major science space instrument of China. Well, the Euclid is already there, so the detection limit of the two instruments are indeed quite close to each other. So they will have a very good detection limit and survey area overlap with each other. And for the proposed JST250 and JPCAM observation, we require a slightly brighter detection limit of about 24 magnitude. So this is already sufficient for our scientific goal, especially for the follow-up observation with JUST. JUST will also be on duty at 2027. And we estimate that we will reach a detection limit of about 23.5 magnitude. So a 24 magnitude detection limit for JPCAM will be sufficient. And using the explorer time calculator and the observation planner, we confirm that we will need 48 nights to cover the area of about 20 square degree for Euclid deep field north. So this is a very initial justification and can be justified later based on some more careful technical justifications. So the final page here is just a Bangkok page. I simply show you, so for detecting the metal absorbers from the IgM, it is probably very difficult using a 4-meter telescope. But in the next generation telescope, such as ELT, TMT, or GMT, this is indeed possible. I'm also working for the ELT science working group, so designed this program. Okay, thank you very much. And I will go back to this page for questions.
Okay, so well, this is something I also I have a question. You said that you will cover a coverage of 20 square degrees, but then on the plot with 89 points, but then on the plot on the right, you see that is in fact.
Wait a minute. So I will need to exit the full screen. So yeah, we will cover about an area of about 20 square degree. So sorry. So this is not this is just showing you this is not 4.8 square degree, but 4.8 degree. Okay.
Well, I don't understand, but I think it's not possible to cover 20 square degrees with all the filters in common with 89 pointings. So the result is more the one on the right. With 89 pointings, you will cover almost 5 square degrees, not 20.
Wow, so I think this figure shows you the strategy. So this is about 4.8 degree, and then for the area is about 20 degrees. So this is a number pointing. This figure is created by the observation planner. So I think it should be.
Yes, but the JPCAM, each one. I explained yesterday. So well, the area in common with all the filters is not the one on the left, but the one on the center on the right.
Oh, you mean not for all the filters covering the same area, right?
That's right. Yes.
Oh, okay. I understand this. So only for the central region, you can cover the central about 4.8 square degree. You can use all the filters. That's understandable. No problem. So
yeah, okay.
for our survey, so it's not for the whole area the same filter coverage. It's just for the innermost region we can cover all the filters.
Okay.
Yeah, so the improvement of the photo Z and also the stacking of to search for the extended emission, that depends on how the exact redshift of the object. So in many cases we don't need all of the filters, but we need a few narrowband filter can still significantly improve the result. So for the justifications here, we assume all the 14 filters are needed, but indeed this is not for all the galaxies. This is just for the example galaxies.
Okay, thank you.
Any questions? All right. Thank you, Yanta.
Mm-hmm.
Next speaker is Alessandre Patekis. He is going to present constraint the late time fill up of clusters.
Good morning. Okay, this is a project that, well, we presented this letter of intent. Joao is my student. He's going to talk remotely in the last slide. So let's see whether it works like that. And the idea is to constrain the latest tale of the star formation history of galaxies in a rather wide range from 0.2 maybe to, well, in principle to 0.7, 0.8 maybe. Well, this for sure, but maybe we can go a little bit far away. And the point is that the key point, let's say, is to make use of this wide field, of course, and the blue filters, mostly. These are the ones that are the most interesting thing for us, although we, of course, need the reddest ones. I'm going to show you the point, the why. One interesting thing here is that by traveling in redshift, let's see how far can we go, okay? But by traveling in redshift and by studying the, let's say, the most recent tail of the star formation history, we are already, let's say, drawing the star formation history through the redshift, at least, let's say, to the half the age of the universe. Okay, so this is or more. This is the point, you know. The focus is on early type galaxies, and as you know, early type galaxies are the picture that comes from the optical range is that they are very old as the universe itself. They form almost in a single burst, almost. Okay. At very high, at least at Z above 2, and they show a metallicity. I mean, the more massive, the more metal rich, and the abundance ratio deviating more from the abundance pattern from the Milky Way. For example, they are getting more massive, more enhanced in magnesium with respect to iron, which is an indication of a shorter formation time scale. Okay, so this is the picture that comes from the optical range. However, if you look here, for example, this is if you can see here, this is the color magnitude relation, okay, or in the optical range, okay, and you can see that the galaxies are on a very, let's say, there is a clear, you know, tiny locus for them. But if you look at this equivalent, let's say, for the near ultraviolet, you can see that this is, well, it's some trend, but it's like a mess. And you can see also in the images, this is an image in the, let's say, in the optical, far ultraviolet, for example, and you can see that you can start to see things, right? So, and this but in the optical, they look rather soft, everything, you know, like very well defined, the clear locus, as you can see in the core magnitude relation, okay? If you look at the spectroscopy, this is the indices some of the key spectral indices in the near ultraviolet and in the optical. If you focus, for example, in the optical, these two indices, let's say this age indicator and metallicity indicator, you can see that the galaxies, these are stacks of thousands of galaxies at resolution 0.4, okay, from the BOSS survey, and the lines are simple stellar populations, and they are rather old and solar or even supersolar metallicity. And you can see that the galaxies, they fall beautifully on the prediction of the models in the optical. And that's why the picture that I summarized at the beginning of this presentation. But if you look at the near ultraviolet, the models, the same models that fit so well here, okay, in the optical, and you could look, for example, at this index with the equivalent width of 12, 10, whatever, okay, drops down 3 times in strength, okay, and it cannot be fit with the single stellar population, with the old population that we see, let's say, from the optical, we derive from the optical range. So the point is that we constructed, let's say, a modeling fitting approach that is composed by this old model that fits so well the optical range, okay, plus like what we call the box, which is constant star formation in the last giga-year. In doing so, we fit perfectly, which are these yellow, orange points, okay, the data everywhere, okay? And what is the fraction that we are inferring, okay, is very tiny, you will see now. But another important thing is that the most important thing in this spectral range is these populations. If any populations in this range, intermediate, let's call it, between 1 and, for example, 10 giga-year, okay, those populations are completely, this small contribution are completely negligible. So we don't care about them, okay? And the contributions that we are deriving are basically something that go from 0.6 to 0.5%. Okay, they are sub 1% contributions. Such a tiny contribution is enough, okay, to fit all the data. And the more massive the galaxies are, the smaller it is. Okay, so if you look here at the best fits that we perform, this is in black is and observe it, the stacked spectrum for these massive galaxies. Okay, and the green is let's say the best fit with the model that I showed you before. Okay, with the box model, we call like that. Okay. And if you look at these components, this is the old component, okay, the red one, okay, and the blue is the young component, this tiny young component, this 0.5%, okay? So if you look now at the ratio, it's overwhelming dominating in the ultraviolet. You see, it's negligible, let's say, above 3,000. But in the ultraviolet, it can be a factor of 10 times brighter than the overwhelming dominating mass population that is old. I mean, just to put you an example, if I switch now a torch, no, now with so much light, you don't see anything. But if I switch the torch in the night, then you see it. Okay, so this is the key point. It's a matter of contrast. And this is exactly the point that we think it makes this proposal strong. So there has been let's say, observation, as I showed you before, in the at Z0.4. Also, we found the same kind of contributions in populations, in massive well, nearby, okay? And also in individual galaxies, in this particular case, a galaxy 3115, and we found a gradient in these tiny contributions. You can see here the mass fraction of young components that is basically zero beyond at a certain distance beyond the effective radius or so. And in the very, very center is where you have this hot, let's say, tiny but hot component. Now, the point is that all we know is in the nearby universe, okay? And the idea is to try to extend as much as possible. In doing so, we can draw also the star formation from these latest contributions. We can draw the star formation in the whole, in this, at least up to redshift point 8, for example. Okay, so this is the idea. Now, we simulated with the J-pass filters how it will look like these contributions. At Z.4, this is the old population, like the ones that fit so beautifully the optical range, okay? And this is where you put a 1% mass of young population. So you can see that there's no difference here in the optical, but this is of course at the redshift frame, no? So and you can see that here we start to see differences that are easily to measure. It could be of the order of 2 magnitudes easily, okay, with the J-pass filters, okay. And so in principle, it should be very easy to do, okay. So that's the point. If we go to redshift point 4, the situation is even more optimistic, okay. You can see here that the spectra, I mean, forget about this red one and just focus with the pink versus the blue. The pink is 1% young, okay? And it's very easy to distinguish. So this is this is feasible, let's say. And the point is that we think that this photospectra and this potential, is sensitive because there is a lot of jumps characteristic in the ultraviolet that can be easily distinguished. For example, you can look here, the 4000 break, but then if you keep going to the blue, you will see all the time jumps. Okay, so this is the information can be very detailed. This is an experiment we did always with the models, okay? And this is at redshift point 8, whether we could distinguish the kind of contribution that is young. I mean, is it younger than for example, this is an old population of 6.5 gig a year, and then another young population, 100 meg a year. So now the question is, can we see younger than that or older than that, but young? Okay, so, and this shows that the answer is yes. You see, this is, for example, if this young contribution is 20 meg a year, or if it is, let's say, older, in this case, 0.5 gig a year. Okay, so it's possible to distinguish with respect to this 0.1% of 0.1 giga-year population. So in principle, there is a potential to break the birth age, birth strength, degeneracy that is characteristic of this population. So we identified this field, and well, this field is fantastic. Maybe after discussion, we will move it a little bit to the right. And this is what you see there. It's the color indicates the redshift. So blue is nearby, and redshift 1 is green, okay? And the size of the cluster, so these are in total 90 clusters, and the size of the cluster indicates the mass of the cluster, okay? Among them, we have 8 clusters that are truly massive, okay? So in principle, well, there is a wide variety of clusters and of environments that will allow us to discuss whether these young components, I mean, what the relation is with respect to the environment, right? The role of the environment as well, not only the star formation history, tail, redshift evolution. Now, what tools are in our hands? We have recently extended our stellar population models to cover not just the near ultraviolet, but also the far ultraviolet, okay? So you can see here newly synthesized spectra, SSP spectra of varying ages, for example, from 6 to 5 giga-year, or 2 or 12 giga-year in the newer ultraviolet. You can see that we can catch Lyman alpha. These models are constructed on fully empirical libraries. There is no theoretical stars at all here. Okay, so these are the unique models in that sense, and they cover an unprecedented range, metallicities, ages, and at the 3 angstrom we have maximum, so it's very high resolution. This is based here. You can see the stars in greens are the ones that allowed us to travel to the far ultraviolet, okay? All from the HST and telescopes, different surveys. Okay, so this is the fitting approach. This we used here. This comes from Luis Diaz. The Mafic code. And this is a fit to a galaxy in the mini J pass, and it is a redshift 0.3, and in red is the best fit, and the residuals in the lower panel, and the conclusion from that fit is that it's 9 giga-year old, solar metallicity, and it has around 2% of young components. So it shows that with a real galaxy that this can be done. And I think now is the time for Joao.
Yeah, can you hear me?
Can you proceed, please?
Yeah. Can you hear me there?
Yeah, loud and clear.
Okay. Hi everyone. Just showing up my face here a little bit. Thanks Alex for the presentation. Yeah, so basically just talking about more of the strategy and the technical aspects of the proposal. Essentially what we did, as Alex said, we got the DESI cluster catalog and tried to find the area where we would maximize the number of clusters in the minimum area, in a sense. So trying to leverage on the big area from the JPCam to observe as many clusters as possible, and then integrating to get these faint structures in the UV, right, as the flux drops in that spectral range. So we isolated that field, and basically using the tools provided, the HOP, and the ETC, we did some tests on like what would be the signal to noise ratio that we would retrieve from this field. So as you see, there's plenty of visibility from November to April in the field we are proposing. A wide variety of clusters. So we would be able to probe not only the redshift evolution, as Alex said, but also with environment and also with different cluster masses, assessing not only the local environment, the impact of local environment, for example, the cluster centric distance, but also the large scale structure. We would be able to also probe the ones that are living in voids and filaments or closer to the cluster centers, for example. The expected uncertainty that we would have is between 0.1 and 0.4 magnitudes, which is optimal in the sense that the UV is so sensitive to these young contributions that this is more than enough, as Alex showed. Again, we would use this strategy to have all the narrowband filters. We need 64 pointings to cover the full area. And we also did two simulations, let's say, two strategies, which would be to use longer exposure times than what is the standard one, the 60 seconds. Trying to see the overheads that we would have, given that we are observing mainly faint sources. And we see that if longer exposure times are allowed, we would be able to, in a sense, save 100 hours of telescope time. So if we could use the auto-guided to be optimal, but I don't know, maybe Javi is not so happy, wouldn't be so happy about it. But I mean, this is something that we could discuss on the time now and the strategy to be used. But that's it. We would be asking around 500, 600 hours of telescope time to be used. I guess that's it. I hope, I don't know, I think Alex is there also to help, and I'm happy to discuss the project with anyone that is would be interested in that. So yeah, thank you very much.
You for your presentation. Any question?
Claro. It's a question for Joan, in fact. I mean, you said that signal to noise about 3, but what is the magnitude that in the... For which magnitude and in which band?
I really cannot hear maybe someone could repeat.
Or
Alex, I don't know, maybe Alex, if you could take the question.
Which magnitude is the one that you used for I mean this calculation?
Yeah, sorry. Yeah. So I used the templates from the ETC, and I fixed a I-band magnitude because it's on the red end of the spectrum, right? So it's like a red stream optical. So I-band of 21 magnitudes in this case. So in a sense, this is the numbers for like the most massive end, for example, redshift 0.8, as Alex mentioned. Yeah.
21 magnitudes in the I-band, which corresponds more or less to... Well, okay. Okay, thank you.
Javi, you are. I'm looking at you.
No, I think you reach. I mean, because it's a lot of time. You reach more.
Yeah, but because it's a 0.8. So
okay.
It's very blue.
It's
I mean,
scale. Okay.
The flash of the
Okay.
Any questions? Right?
Yeah, Rosa, go ahead. Rosa, you can unmute yourself.
Do you hear me now?
Yeah, now.
Sorry?
Yeah, we can hear you.
Okay. Well, thank you for the presentation on the project. Sorry, but I didn't hear well the magnitude that you needed to the magnitude limit that you needed for this project. Also, because I would like to know why this research cannot be done with the data that we have already with JPass. I know that the field it is not in the JPass frame footprint, but I mean it can be done with another cluster that we are detecting a lot of cluster in this range of RESI between less than 1, between 0.2 and 1 in RESI.
So I did estimate the depth regarding JPass, but it's because it's so for example the I-band criteria that I use of like having 21 magnitude more or less basically meant that in the UV you are dropping maybe 2 even 3 magnitudes lower, let's say. So that's it. We essentially you just have to integrate more time than what the depth of JPass. I don't have the numbers with me right now, but that's it. Essentially, you have to go deeper than the I think it was like 22 something, right? From I don't remember now the JPass numbers, but we would have to go some magnitudes fainter than than the survey would reach, let's say.
Okay, well, I think this is a very important point that you work for the proposal, because I mean for the RESI range that you are needed to observe, it is already covered by all the JPass data. So that means you needed longer exposure time to get deeper in the blue band that we are not getting. It is important that you answer this properly.
Okay.
Thanks, Rosa, for the suggestion where to put the emphasis. Thank you.
Thank you. Yeah, thank you so much.
Thank you.
Thank you. I'll mute myself now. Thank you, everyone.
Is Luis Garcia. He is going to present the Pican studies the Virgo A.
Okay. Good morning, everyone. Thank you very much for attending this presentation. Well, my name is Luis Garcia, and I'm going to present the proposal that we are proposing. And I would like also to mention that I have been working also with Rosa González Delgado on this proposal. The chance is also presentation. So, and we are also working with many people from the JPass collaboration. And we propose to observe the Virgo galaxy cluster. But why Virgo? Well, Virgo cluster is a massive, very massive galaxy cluster in the local universe with a mass that is estimated about 5 times 10 to the 14 solar masses. And actually is the dominant mass concentration in the local universe. For this reason, typically is defined as the center of the local supercluster. And as such, the Virgo cluster also is the nearest and richest galaxy cluster close to the Milky Way. And for this reason, the Virgo cluster and its galaxy members has attracted a lot of motivation to study them. But far from exhausting the topic, the study of this cluster and these galaxies has motivated many current researches and even current services such as the new generation Virgo survey. And also for this reason, the Virgo cluster remains as a benchmark instrument for tracing galaxy evolution studies and interactions at the local universe, as well as for investigating the hierarchical growth of the structures of the structures in the cold dark matter dominated universe. But as Alessandro told us yesterday, it's not included in JPAS. However, observing Virgo is really challenging. The first reason is because the area in which lies this galaxy cluster is around 140 square degrees, really, really big. And for this reason, and also because this galaxy is very rich, an efficient spectroscopic follow-up of all these galaxies is really, really hard. Especially because owing to the distance of this galaxy cluster, some of these galaxies are really, really big. The projected size of these galaxies is even bigger than 1 arc-minute, which is the typical field of view of modern IFU instruments, and also challenging for very low mass galaxies that are very, very faint. However, with GPCAM and GPS filters, we are in a unique situation in which these instruments, and probably this is the only facility around the world, around the globe, that for which is possible for overcoming all these limitations, as is unique suited for observing the Virgo cluster. And for us, we are making this proposal because we have a unique opportunity of creating a legacy dataset of it. And how do we plan to do so? Well, we are thinking in using the same strategy that JPAS. This is mainly for two reasons. The first one is because in terms of area and depth, these exposure stands are very efficient. And the other one is because we have a large experience working with the JPAS catalogs and images, so we know all the capabilities and all the limitations in order to set what we can do to add to the scientific community. And for instance, as a result of all this analysis, as I mentioned, we are many people from the JPAS collaboration, we can state that using this exposure times, we can reach limited magnitudes for galaxies up to magnitude 22.2 in average. And also the limiting surface brightness of the images is set around 25 and 26 magnitudes per second. And also we have we took a look to see how is the visibility of the Virgo cluster, because it's low in elevation with respect to it's lower than the JPAS footprint, and we stated that it's possible to observe the Virgo cluster between March and April during all the night, okay, with an elevation above 40 square degrees. Okay. And also, in a worst case, we can extend the observations even to February and May. But still, with the available observing time that we have, it's not possible to observe the full footprint of the Virgo cluster because it's too big. So we are thinking in a strategy to focus on the upper parts of the Virgo cluster, which is referred as Virgo A supercluster, where the center is M87, that is here, and here we can see Virgo B subcluster, where the center is M49. So the area of Virgo A subcluster is 100 square degrees, which is still big. So we are proposing to observe a substantial part of this subcluster. In particular, we are thinking now in the first strategy that we observe around 50 square degrees of the northern part of the Virgo A subcluster. And the expected total observing time will be around 750 hours that are distributed in dark, also bright time, because we are using as a detection band the I band, which is the 35. But we are at the same time we are still exploring more possibilities. So this footprint is not the final one. For instance, we are also thinking in something a bit more complex, like a pros, because for us it's very important for our aims that I'm going to show now, to have images from the inner part and outer part, and also along radial directions. Also here we can see that this strategy is much more efficient in terms of area for the Virgo cluster, and still we are working on this. So our main scientific goal is to perform a full comprehensive analysis for the Virgo cluster from a perspective, independent of but also complementary to previous surveys. As we are there is a large number of collaborators here for this proposal. We have here, I'm summarizing the main scientific topics that we would like to explore. The first one is to explore the stellar content and the stellar formation histories of Virgo galaxies, especially putting emphasis on the spatial reference of galaxies of Virgo. But why? Well, due to the JPAS photometric system, we are going to be able to retrieve low-resolution spectrum, okay, like an IFU-like study for all the galaxies in Virgo, with a spatial scale of 80 parsecs, assuming a PSF of 1 parsec. The advantage of this is that we don't have any kind of redirection of our galaxies. We don't have any kind of aperture effects, which are really advantage with respect to IFU spectrographs, because we are going to observe many galaxies that are larger than 1-2 arc minutes, and also the limiting surface brightness is typically much lower, much deeper than IFU spectrographs. Here, to illustrate this, we can see a galaxy from Manga, and this little hexagon is the field of view of Manga. However, with JPAS-like data, we can extend much more the photospectra that we can obtain from these very, very big galaxies. And our idea is to use the set of techniques and methodologies that we have developed during the last years, for instance, by 2D JPAS, and in order to perform our self-fitting analysis, or using our regular codes from the JPAS collaboration, in order to set constraints on the star formation histories and stellar population properties of these galaxies. In addition, needless to say that we can extend also this analysis to the integrated properties of all the Virgo galaxies. But also we can extend this analysis to low mass galaxies and dwarf ellipticals. As you know, these galaxies in high density environments are very interesting, and as we demonstrated in theJST250, we can extend the analysis up to the stellar mass range of these galaxies. Here is the stellar mass completeness of quiescent galaxies and star-forming galaxies from mini JPAS, and you can see that we can reach this stellar mass range easily. In addition, we are interested in studying the ionized gas properties of the Virgo galaxies using JPAS-like data, as in this proposal. So, in this case, Ginés Martínez OAJ, who is also a member of our group at the OAJ, developed during these years some machine learning techniques, and more recently a foundational model dubbed Ojalá, in order to retrieve from JPass photospectra in order to retrieve equivalent weights of emission galaxies. It will be really very useful for us because we are going able to classify and characterize emission line galaxies, and at the same time we are going able to study the distribution of these star-forming regions across spatial resolved galaxies in the Virgo cluster. But also, some of our collaborators have been checking that it's possible to also extend all these studies to globular extragalactic globular clusters. For instance, if we put emphasis on M87, which is the center of the Virgo A subcluster, some deep imaging always using in the past broadband imaging detected that there are more than 13,000 globular clusters in M87. However, due to as these globular clusters are typically faint, that in the literature we can only find around 700 spectra of this globular cluster. However, with the depth that we expect using the JPass observing times, we expect that we are going to get around 4,000 the spectra of 4,000 globular clusters only around it, which corresponds more or less half of the globular cluster luminosity function of this massive galaxy. In addition, we are also interested in constraining the properties of the diffuse intracluster light of the Virgo cluster. As our typical limiting sulfur value of this image is set more or less between 25 and 26. Sometimes these numbers sounds like okay, it's not really deeper, but due to the distance of the Virgo cluster, these limiting magnitudes are going to allow us to retrieve also the photospectra of the intracluster light. Okay, so the advantage of these images also is that we are going to observe very large areas of this component of the cluster, because as we know, there are a lot of campaigns from HST to explore this component, but the problem of HST is that the field of view is really tiny in comparison with the field of view that we will have with this observation. So we will be able to constrain the photospectra of the intracluster light in a very large areas in order to complement more smaller areas and deeper, for instance, from different campaigns of the HST. And finally, some of us, maybe you are asking, okay, but this area is very big and there are thousands of galaxies. What happens with the galaxies in the background? We are going to analyze, to study them also to complement this study. So the idea is to start a new kind of methodology that I started during my first postdoc with Professor Keiichi Uematsu and Tom Borjas. And the idea is to create magnification maps of the Virgo cluster in order to set constraints on the geometry of the dark matter halo of Virgo. So this technique is still in development, but we predict that it's going to be much more effective than traditional techniques, okay, based on number counts, and also this is going to help a lot to alleviate the massive degeneracy from weak latency, okay, typically here, in order to set better constraints on the geometry of the dark matter halo of Virgo cluster. And just this is the last slide with all the conclusions. Also, like I think I forgot to mention that. Okay, that with this proposal, the spatial scales of the photospectrum that we are going to get, 8 parsecs across all the Virgo cluster. And also, we expect that with this proposal is going to yield dozens of papers in few journals, and we have a large team to work in all the topics that I presented here, and also that we have developed already many tools and techniques in order to start to analyze all this data as soon as possible. Thank you very much.
You for your presentation. Anyone have a question?
Thank you so much. By the way, excuse me, I don't have much voice. So you mentioned intra-cluster light on those surface fragments, and I think you gave some limits between 24 to 26 max per
25, 26.
25, 26. So my question would be, have you done some numbers on whether the scope of the project would benefit from going deeper and achieving surface brightness of the order of 29, something like that?
We didn't make numbers, but the problem is that at this limit, increasing you want to go deeper, the price that you pay is that observing time increases. And also, there are more goals in the project, because we don't expect to have the intercluster light very far. This is something that I started to also discuss with Joyce since the start. And at least now for her also it's quite interesting. I mean, with this deck, we can go deeper. Yes, something that increases really a lot.
So why? Thank you. Okay. Next speaker is María del Carmen Argudo Fernández. Going to present a GPAS analysis of cavity galaxy legacy survey.
Hello, good morning. Can you hear me well?
Yep, you can share your screen.
Okay, I'm gonna try to share my screen. Okay, 5 minutes. Can see this. All right, I think I have. That's okay.
Okay, you can try full screen.
On that, but I'm not sure how.
Prefer to go like this. It's okay.
Okay, probably gonna leave it like this. All right. So yeah, good morning, everyone. And thank you for the invitation to present the project that we sent as a letter of intent. I'm sorry I couldn't visit and stay in place because of very bad logistics from Granada. It has been very difficult for me to go. So I'm going to present this on behalf of the GALS team. This is a project developed mainly from University of Granada with strong support of many members of the cavity collaboration, including people in the IAJ and University of Lyon, people in the ISC, and also people from Chile, here in the Spain, University of Cordoba as well, and people in University of British Columbia and people from Iran. All right, so what we are proposing is to observe void galaxies. So from the early universe to the present days, we know that as the universe has been expanded, then dense areas in the universe has become even more dense. On the contrary, the low density regions of the universe has become even emptier, representing in the present universe, both represent 70% of the universe volume of the present universe. They still host galaxies. These galaxies are unaffected by high density environment processes that are typical like in the cell environments. And these galaxies are still accreting gas from the intergalactic medium, offering pure look as a cool mode for assembly mechanism. So the cavity project is the Calar Alto Body Integral Field Tesseract Survey is the first study, the first collaboration to perform an homogeneous and systematic analysis of a well-defined sample of void galaxies using IFU data. The sample is based in a very well-defined characterized sample of 15 voids in the nearby universe. And from it's still not has revolutionized, but it's still revolutionizing our knowledge of void galaxies. We know, thanks to the cavity project, that void galaxies assemble their mass more slowly than not void galaxies at a given stellar mass. It was the best, not the best, the first impact result of the collaboration with the paper published in Nature in 2023. The second more impact, probably exploration of these voids. The result is the identification of a sample of quaint and isolated dwarf galaxies in voids. That is a population of galaxies that shouldn't exist in voids. And based on the analysis of the first 200 galaxies from IFU data, Ana Conrado in the IAA in 2024 and 2026 has found an evidence of younger disk and higher gas fraction in the outer galactic regions of these galaxies. So this result is what is supporting why we want to use JPAS data to do the analysis of cavity galaxies. So IFU data, as Luis has found, as shown, is limited to the inner region of the galaxies, while JPAS capture the full spatial external surrounding of these galaxies. The unique J spectra with a unique narrow band filters provide this IFU-like spectra for every pixel in a larger field. So our aim is also to study the substructures within the voids and also the low surface brightness regions around these galaxies. So it provides a unique sensitivity to the diffuse and low surface brightness features like filaments and tendrils even within the voids. So our target is this void 738. This is a void that in this figure here is located in this inner region in the Hercules void. It's located in a region that is surrounded by the Hercules supercluster and the Coma and Virgo as well. And it's an area with this dynamic map is showing that it's an expanding region in the local universe. So this region is particularly interesting to studying the cosmic web, tracing this structure from the Hercules supercluster inside into the void through filaments and tendrils that can be identified in this void. So there, in this sense, we think that there might be some overlap with the JPAS footprint. Also, this area, we don't know if it will complete the coverage of this area. Also, our observing strategy is a little bit different because we need to go deep for this low surface brightness at the outskirts of the galaxies. So the aim of the proposal is also to contribute to the overall survey by focusing on this region. In this context, this void is representative as well of the void sample. It has an average void density considering the number of galaxies in this void that is around 155 void galaxies, and a typical size of the voids is 15 megaparsec. This void has an effective radius of 17.6, so it's pretty much representative of the voids of the cavity void sample. This void also presents internal tendril-like substructure, and I will talk about it, I think, in the next slides. So the main scientific objectives of our observing project is to determine how these tendrils and groups influencing the mass assembly histories of the galaxies, also to explore the dependence with the larger scale structure, to establish galaxy property dependencies in comparison with galaxies in large scale environment, that we can perform a similar analysis for galaxies in denser environments, and overall to identify which are the drivers for galaxy quenching in these underdense regions of the universe. So we aim to do this, mapping the stellar population of the galaxies. So as I said before, the J-pass, the J spectra allows to perform stellar population analysis. We base this analysis of SCD fitting and to get the formation histories using techniques as SIGAL or by SIGAL that Chris has also shown. This not only provide information on the stellar population, but with some procedures that has been performed within the JPass collaborators or mini JPass has shown that we can also estimate stellar metallicities and ionicity gas properties, so we can do some radial profiles and 2D analysis of these galaxies up to several effective radius. Also, we can use spatially resolved gas diagnosis diagram as the BPTN1 to identify which are the main ionization mechanisms for void galaxies in comparison with galaxies with denser environment. Okay, so passing to the observing strategy, this void has in the lower declination shows some areas with overdensity. So we are interested on these two regions in particular. We call them the region Jacals A and Jacals B. We have selected this because first we have identified the presence of galaxy groups. The richness group in void is up to 6 galaxies. In this case, we have found in this region B a group up to 5 galaxies, at least galaxies members that we can observe because they are bright enough to be observed by the SDSS, but maybe there are more neighbors that are deeper, so we couldn't get an estimate the redshift for these objects. And also the idea is to complement with an approved observing program with MIRCAT, where we are obtaining resolved H1 maps around some galaxy. That is, this will be performed within 1 degree around these H1 centers. These are galaxies, massive galaxies with H1 observed in alpha. And these are mainly located in the regions where we are finding these groups, and they looks to be distributed in this tendon-like structure in the void. So that's why these are to the region that we are interested in to observe. Since we are interested in the low surface brightness features at outskirts of these galaxies, we require slightly larger exposure times than in the JPass survey. We have based our estimation requiring a minimum signal-to-noise ratio of 2.5 within a pixel in the 550 filter, reaching magnitude of, well, in this case, surface brightness of 24 magnitudes per second square. This table summarizes a little bit the information of regarding these two areas. This estimation has been performed for dark time. We also have estimation for gray times that we present in the letter, increasing a little bit the time. Unfortunately, the bright time estimation provides unreasonable exposure times, and we are only asking for the narrow band trace, not the the SDSS filter because this area is already covered by the SDSS, so we can reuse that information in this case. So regarding the connection with the H1 observation, these two areas easily complement the H1 observation that, as I said before, will be observed within 1 degree around the MidCat centrals, which also increase the legacy value of this program. Also, the combination of not only the H1 observation that we also have CO maps of some of these galaxies from IAM and from ALMA, dedicated ALMA concavity program. And in combination with the Optica and the stellar population at these large areas around the galaxies, with these deep images will also allow to estimate the dark matter content of these galaxies within the voids and in the connection with this large, well, not large, it's large structure within the voids, but in comparison with large and denser structure and like very low density substructure within the voids. Yeah, so maybe I went a little fast, but it's okay because I would like to have some discussion about the program. This is my contact in case that you have any question. Also, regarding Cavity, this is the webpage of Cavity. The data release 2 is incoming. We are releasing 100 galaxies with IFU data. With the previous data release, this is a total of 200 void galaxies with IFU data. So I hope that you find it interesting and enjoy to play a little bit with the data. Yeah, I have a few more extra slides for the question in case that your question goes this way. We have the pointings that we use for these two areas using the full trace over the narrow bands, and the visibility mainly will be very close to the Virgo because the void is close to the same region of the sky. The main observability optimized between March and June. And yeah, that's it. Thank you.
For your presentation, anyone have
Es que no hay. La repites tú. Venga. Okay. Hi, Mike. What is the exposure time you put per exposure? I mean, per pointing or per.
Oh wait. I have a mix here of things. Yeah. So about the exposure time, sorry, per pointing.
Per exposure, because you said you need 247 pointings, but yeah, I don't know. Yeah, how many exposures do you need in each trade?
Oh yes. Oh, that information I have for it.
Sure. Sorry, I can later.
Yeah. So yeah, we had to redo the calculation because at the beginning we were considering exposure time of 300 seconds, and now we know that the limit is 100. So we need to redo this. But at the beginning we estimated 15 minutes divided in 3 exposures of 300 seconds. So with the two beginning to a beginning of 2 and 3 of 300 seconds. So we need to change this a little bit for 1. So that will be 50 of 100 to reach, I guess, but I need to do the calculation with the estimator.
Okay, thank you. And how many filters do you need for stellar population analysis and the minimum? I mean, the thing is that you have calculated these numbers with the 550 filter, which is where the galaxies have like higher signal, especially at the rest of the void. And so I don't know, how many filters do you need? The minimum one to do the analysis you are proposing.
Well, I'm not sure. In principle, we choose the 56 because we were like trying to mimic as much as the JPass because that is like thinking about the complementation, the complement um, of the observations, and also to compare stellar population for the void galaxies with the galaxies in denser environment that we are not going to observe. We will use this information from JPass data. So in principle, if they are using the 56, we just are proposing the 56 filter, but maybe we can use less. I'm not sure about this. Maybe I should talk with people in JPass, with the expert, so we can maybe that will allow us to reach lower times, maybe lower the need of lower estimation time, exposure time. I'm not sure. Maybe that's your question, that maybe we can reduce this time by choosing another set of filters.
No, I was wondering, I mean, I was just, I don't know, just asking my curiosity, yeah.
Rosa raised her hand. You can.
Okay, well, thank you, Mame, for the presentation of the project. I only want to clarify the last point, because we were discussing many times for a long time in the Galaxy Evolution JPass Telecom. So, I mean, for Galaxy Evolution, we need all the filter, because we had because for the distribution of the filter in the 4 trays, although for you can say, okay, well, I don't want to observe, for example, the red part of the spectrum. For example, in the case that you have object, as it is the case, a low resi. However, the trays always have the 4 filter at the center that correspond to the blue. So that means that in some way, and according with the resi, always you will have some absorption line or emission line that could be in any of the filter trays. So my advice for all the people that can apply for this, at least that is that you apply for the whole filter system, because in other case you always will have holes in the spectra, and in that case will make more difficult to have homogeneous data. Well, that's my advice.
I mean, my question was with the exposure time. I mean, you can actually expose all the filters, but maybe if you need to reach a signal, it's just what it was more related with the analysis. I mean, I agree with you, yeah, but it was it was more related with exposure time, because if you need to have like very high signal to noise in all the filters, well, it's not the same that if you need to have them in a, I don't know, in a given range, or in a given range, you just can do your analysis, no? You know, I don't know, yeah.
You mean that well,
it might be understandable. Well, it doesn't. I mean, in general, I agree with you, but I was wondering, depending on the analysis, you really need to have like specific filters with a high signal to noise or with a signal to noise above certain level, or all of them. I know that at the end, you're gonna have them. Yeah, you're gonna have them all by the way they are building the train, and it's better to have them all. But yeah, it was more related with the exposure type, with the signal to noise, Rosa.
Yeah, okay, but I mean, the problem is how it is located, the filter in the trace system, in the trace. So that means that you always have a miss of red and blue filter. So that means that maybe when you start with the individual filters, you can estimate the individual exposure time for every filters. But in that case, it is difficult, and in other case, if you miss the exposure time, in that case, also you can have a no homogeneous depth in in the system. But I mean, well, anyway, everyone has to know what they want to to do. But I mean this is our experience with several year analyzing JPass data, and also because we have discussing many times in the Galaxy Evolution Telecom, because there are projects where they prefer to serve only in a few trays and 2 trays instead of the whole filter system. So that means that this is something that we have discussed a lot, and at least from the Galaxy Evolution in general perspective, we don't want half in the spectrum. So that means that we need to observe with all the filters to get the most homogeneous data as possible.
Yeah, and I think also that the most critical
I will send you by email. I will not gonna Jack.
I think that the most critical point is the get of the
I will ask to you later by email.
yeah. Okay. So you hear me? Yes? No?
We can hear you.
You can hear me? Ah, okay, thank you. I wasn't sure. Yeah, I think that the most critical point of this is maybe not much stellar population like the age or stellar mass. I don't think that the impact is too high. But in the case that we want to go into the nebular abundances analysis, that is going to be a bit more critical. I think that in the procedure by Martinez Olaisen, this shows that maybe it's very critical, probably the use of all the filters to do this analysis. Otherwise, probably is not possible with this low resolution spectrum.
No one else? Thank you again.
Thank you.
Up to 11 at 3.
So for those people online, see you at 11:35.
Hi, everyone. Next speaker is Patricia Sanchez. She's talking about Qatar City.
Okay, thank you. First of all, I have to apologize because I cannot access the presentation that I prepared, so I put some slides together. Well, this is gonna be a little bit not complete. Okay. And I'll start for what we propose to do. We propose to observe two fields of 9 degrees squares between the JPass footprint, so something that is inside, so we can take advantage of the already observations to reach like a 2.4 magnitude deeper than the main survey of JPass. And the main motivation, the main scientific motivation for us is to characterize the growth of clusters, the growth of structures at the same time than the evolution of galaxies in there, no? But all together, no separately. So we preselected several fields which are within the JPass footprint, as I mentioned, which has been selected to maximize the number of clusters, of massive clusters with masses above 10 to the 14 solar masses, at redshift between 0.15 and 0.3. And I will explain later why we chose that redshift range. But of course, in the same field, we will find also with the redshift at higher, in those fields, we will find redshift at higher, we will find clusters of higher redshift, sorry. These 7 ones have been selected because they can be observed, they have a visibility for several hours during the night, and they reach like high altitudes, above 15 degrees, and well, they cover the whole year, but we only would like to observe, or we only propose time to observe 2 of those areas, not 7. And we are flexible as well in the specific fields. So this is an example of one of those areas. Each circle here represents a massive cluster with masses above 10 to the 14 solar masses. As I say, the color red here represents the redshift, and the black circle the 500 radius of these clusters. No? Okay. What do we want to do this? No? Well, most studies of the influence of the environment in galaxy evolution are limited to compare star-forming galaxies versus galaxies, maybe with radius or a different redshift. Or normally, yeah, they compare the distribution of galaxies at different times, no, with radius and with redshift, and maybe with density or mass of the cluster, no. But these studies are missing what really happens to the galaxies, no. For what? Oh. Since they enter into the cluster. So the galaxies, much before reaching the virial radius, they found this gas that is the pressure shock of the gas of the intracluster medium, and that already has a high impact on the galaxy, probably removing most of the gas that is in there. Huh? Then the galaxies are accreted also in group and reach to the center, where the different mechanisms that happen when they reach into the cluster have different importance. No? So, for example, around pressure stripping is very important, but only in the most dense regions, while flyback interactions are very important, no? In the info, where the velocities are very high in the info. No? So, if you want to capture all these different physical mechanisms that transform galaxies as they enter into the cluster, you have to map like a large regions, and we study also the local environment, no? So the density of the gas, if the gas has a superstructure, or if they have pressure shocks and things like that, no? So that allows you to compare with like the global environment that is probably related with initial conditions, the mass of the cluster, the richness, etc., with the local influence of the pressure, the temperature of the galactic medium, etc. So the redshift range that we chose is between 0.15 and 0.30, and It's mainly for two reasons. Because, well, it's a period of time that where the massive galaxy clusters grow a lot, no? Since Redshift 0.3 to now, it's estimated that very massive clusters have accreted 40% of the total mass. This is a phase space diagram, no, with the relative line of sight velocity in a cluster versus the cluster-centric radius. And here you see the redshift where galaxies are accreted, no, since when. And so what you have here the galaxies that were accreted long time ago, and this blue ones that are influent to the clusters are recently accreted. And on the other hand, the redshift 0.15 is the minimum redshift where we can start to observe the blue and near ultraviolet part of the spectrum. I don't have to say much about this because Alex has talked a lot about the importance of studying these trends. Those are stellar population synthesis models with different ages, no, from 3 megayears to 3 gigayears, no? And you can see that in the near ultraviolet, the variations in flux are very large, no? So by tracing this range of the spectrum, we will have much more sensitivity to variations of the stellar populations, and that will allow to also to distinguish. Sorry that I'm not very ordered because of the representation. That will allow you to distinguish as well the different mechanisms that are acting, transforming the galaxies that act in different time scales. It's not the same ramp pressure stripping that act in 200 megayears, that other mechanisms that can last us up to 2 gigayears, no? Well, and if you go to the main JPass survey, which you can see that this is they represent the red represents the spectrum of an old galaxy at redshift 0.15 and 0.30 and 0.3, no? With different ages depending on the redshift, and normalized to R22 magnitude. So for a galaxy of 10 to the 9 solar masses here and 5 10 to the 9 solar masses here. And here are the magnitudes in the different narrow filters of JPass. You can, this is like 22 more or less, no? I put it like the limit of JPass, and you can see that you can detect the galaxy in the red part of the spectrum, but as you go to the bluer magnitudes, you start to miss these bands, which are the most important, we say, to detect these transformations of galaxies as they fall into the cluster. No, here you can see what something similar to what Alexander saw, which is the young population, and here is the population plus 1% of a mass of young population. No, and you can see that the differences start to be seen in the near ultraviolet. Okay. Well, this is for one side, and another side that we want to study or what we can do. Some of the things that we can do, no, with these surveys, I haven't included them all because it's this problem with the presentation that I told you. One is to study the mass accretion rate. As I told you, we want to study the transformation of galaxies at the same time of the formation of the cluster, no? So one of the important things are the rate at which the cluster are accreting mass and are growing, no? Furthermore, the mass accretion rate allows us to test the cosmological scenarios because there are clear predictions of how this depends on the properties of the clusters and the cosmological parameters. No. Okay. So one way to do this is to study the density distribution of galaxies at what is called the splash back region. The splash back region is the region where the galaxies reach the first apocenter as the first reach of the apocenter, no, when they fall into the cluster. And beyond those galaxies, all the rest of the galaxies are all infalling, no? They haven't been part of the cluster, and in fact has been proposed like a limit to much better limit, no, of the size of the cluster than, for example, the R200 or the R500, no? So cosmological simulations, and many of them predict that this, you can see this black splash radius as a drop in the density profile of the clusters that can be traced, for example, with the number density of galaxies, no? And so these are this is the profile of the cluster. This is a drop. Okay, this is the outskirts, and these are the result with a different mass accretion rate. Okay, the red, the blue, and the green. And yeah, this, if you normalize it to 200, are in different scales. Not none. So many studies have been trying to study this or to find this drop in the density, and they have found it. But spectroscopic studies. This is a spectroscopic study of phoneme. This is one of the predictions, and this is what they found with the galaxies. It seems very nice, but they have to stack a lot of clusters, okay, with different properties, so it's not ideal. They did it just in fact to see if they can find it. There are some studies that have found this drop as well with photometry, but they found that the radius is very small, and the peak is due to the contamination by non-members. No? There are other issues as well with non-sphericity and projection effects, but we have already tools to solve those issues, by the way. So ideally, we want to have like photometric studies with capacity to detect the membership of the galaxies without the need to have to do a spectroscopy, no? And to reach this, we need to reach the deeper magnitude to trace the blue part of the spectrum. Otherwise, the photometric receipt, which is not going to be accurate enough. This have already talked about this. Is the galaxy transformations. We need to detect the different mechanisms to trace also the ultraviolet. As I say that we are already, because this was part of the catastrophe study that we were planning to do at the Caralto, we have a lot of complementary data and unclear that we can use for this survey. No? For example, we are collecting, well, not with Toltec now, but right now we are doing with Nikita in Granada because Toltec has several problems. But we are obtaining millimeters observation at 1.1, 1.4, and 2 millimeters. We have already time, but now Toltec is broken, as I said, but we are already observations with Nikita for 2 clusters that allow us to do Sanjayev-Feldovich analysis with a much better resolution to what's the usual, no? Which is 800 resolution. Why this is important? Because it will allow us to detect like the presence of shocks and shock structures and prove the gas dynamic, which is very related also with the past history of the cluster, you know, and this has not been done before. And we are also we are collecting now spectroscopy of galaxies in clusters using the Subaru point focus spectrograph, which has a field of view of 1.3 degrees diameters, and it can have a multiplexing of 2,394 targets in science. So we can get a lot of galaxies. But again, this is an example of an observation that we have for the cluster Abel 2390. But the problem is that when we go a little bit to the external parts, we have a very large percentage of contamination. In fact, despite this, for example, these targets were selected with a large, with a multi-wavelength photometry and with a wide coverage in wavelength, the success rate was only of 23%, thanks to a magnitude of 21.5. Sorry, I deleted it, especially in the external parts. No, so for this, it will be very important again to have the JPAS photometry. With this spectroscopy, with the analysis of the submillimeter, and with the JPAS photometry, we can do estimations also of mass for this cluster with different techniques, which actually are optimal in different radial ranges. So improving many of the problems affecting determination of the mass. Okay, I think the legacy study of these observations it's been proved already this morning, because I think, for example, the project proposed by Alex or proposed by Lee can be done perfectly at the same time as this one. All of us want to have deeper observation of a given field. We chose the areas between the JPAS footprint because we have more observations already. Like the JPAS can be added to these new ones, no? But in reality, we wanted to maximize the number of massive clusters between those residues that I told you, but in reality, the project can be done in other fields. It's true that we have some complementary observations already done for some clusters, no? So ideally they will contain these clusters. For example, apart from this project of this cluster, yeah, the Alice project at higher resist could be done or begin. For example, studies of the luminosity function, no? But there are already some studies of the Lyman alpha luminosity function by Torraba Torregosa, but they cover more or less, especially when you go to higher resist, the quasar regime, no? The high luminosity Lyman alpha function. With this observation, we could extend, no? To the regime where with the luminosity function start to be dominated by galaxies. So the strategy, what we want to observe in the fourth trace, the 1, the 2, the 3, the 4. I don't know if this is correct. I mean, I have to now see your talk and do everything again. And in fact, there is possibilities for this project that we don't need to put the, I mean, maybe I have to check that we can maybe for some trace to put more exposure time down for others. I don't know. But for now, what we calculated was 64 pointings with density of 0.236 per field, with exposure time of 6,000 each. And I know that this is preferable to be 100. I think I would have been enough 2.2 or I'm not sure. And so that will be the total amount of time per field. So if we want 2 fields, we will have to double this exposure. But I have to say that we can do a lot of science as well with just 1. If we put 2, was also for other studies like the luminosity function, things like that will improve the legacy value with larger areas. No? Well, this is a little bit of the summary. Well, I propose that now, like very quickly. We propose to perform the observations of 2 areas of 9 degrees squared each between the JPass survey footprint. We are interested in studying the growth of the structure at the same time as the transformations of galaxies in it, so the connection between galaxy evolution and large-scale structural formation, studying both the local and the global environment. And that will allow us not only to study this issue, but also to improve the mass density profile using different techniques, etc. Don't read because I just read. 1 second, I want that's it.
Thank you. Anyone have a question?
Alicia, thanks for the presentation. I have 2 questions, if you don't mind. One is related with your pointings and the ancillary data that you commented on. How much this extra data constrain the pointings, and somehow related with what you were saying, that this project can actually somehow relate with other projects that are being presented?
I mean, the thing we have the. It will be nice also that this also was selected. I didn't say anything, but because they have some ancillary data, which is not. I mean that can be fine. It's important that they have X-ray or that, for example, in the Rosita in the future, not actually now. Or and we also selected it because some of the classes have HSD or other something. Right. Okay, but for the ones that we are collecting for now, we have only 2 clusters. It's 2 clusters because they are not a field. I mean, the field of view, is much lower. So we have like 2 clusters with spectroscopy and 2 clusters with some millimeters, and one of them is the same. No? So it's not. It could be done with other fields. So it's not. It's not crucial, no. But yeah.
The other question is, if the chair allows, can I ask another? Since the data are within the JPass footprint and you're planning on using the first JPass pass, are you considering the option? Now I'm speaking as a JPass member. Are you considering releasing this as extended JPass
Of course.
So something like
of course, of course. I haven't done yet, of course. I thought it was a compulsory, no, for the last service, no? Well, in any case, yes, of course, yes, we are. I mean, my policy is always release everything. I mean, I don't, without any time for. I mean, I don't have time to do anything, so I'm sorry I didn't. I mean, because I did that very quickly. I didn't put the team that is already involved, but yes, a lot of people involved here that I didn't put their names. Sorry. But yeah, I have to make the presentation here in a month. But yeah, no, my policy is always like data has to be free. I mean, there's plenty of things to do with the data, and we are the Spanish community, we have to support each other. And so
Yeah, because
even the complementary data, so everything that we have served, yeah.
I was thinking about the interaction with the data analysis department. Because at the end, if this gets merged in JPass, I wonder if it's easier or whatever.
So obviously it will be easier for sure. Yeah. No, of course. I mean, I was counting with it. Yeah.
Right.
Stefano has a question.
Yeah, thank you very much. Can you hear me? Yeah.
Yeah.
Okay. So thanks for the talk. I have a suggestion more than a question because, well, yesterday I wasn't present, so I don't know exactly where are the project put in the sky. But I think one of the goal of this meeting is to try to talk between all the teams and discuss possible best strategies. And today we have a project that is about the Virgo cluster that is observable in spring, one about voids that is observable in springs, and also the project I'm going to present about the Hercules cluster, also visible in spring. So I guess that maybe you can choose your field, since your fields are available along all the sky. Maybe you can prioritize those that are observable in a different epoch of the year, so that we can basically.
I mean, it's true that I would like to serve the observation between the two, the autumn and spring, so it can be done faster. but it's true, yeah, of course. I mean, I guess.
I mean, this can be a criteria for deciding. Just this.
Okay, I have that. Yeah, have that in account. So I think when the Euclid did, do you remember where it was as well?
It's
I don't remember.
It's the most ecliptic pole. She's up left.
Okay.
Okay.
In the two. Yeah, sure. We can divide the deep with the surface. One for the screen and the other for the.
So, let's pick Stefano that he is talking about the DIPA new Hercules super cluster.
Thank you.
Do you want to share your screen, Stefano?
Yes, I already did it. Do you see it?
Yeah, it's going. Okay.
Let me see it. If I can put it in presentation mode. Yes. Okay.
Yeah. Perfect.
Okay. So thank you very much for this talk you gave me. I'm sorry that I'm not there, but I'm well, most of the time on paternity leave yet. But in this week in particular, I'm at another meeting. And I am in a remote island in Italy, in the south of Italy, so my internet connection is very bad. So I try to be really short and concise because I fear that the connection can get lost anytime. Okay. So the project that I'm presenting is called the JPass style view of the Hercules supercluster. I reported here some of the collaborators that are included: Alfonso Aguerri, Antonio Calero, Lorenzo Morelli, Virginia Cuomo, and Enrico Maria Corsini. These are basically the team that participated to the starting point of this project, because last year in the regular open time call, we participated with asking for observing one of the three main clusters of the Hercules supercluster, that is Abel 2151. You can see here an image on the left of the situation of the supercluster. So you see that Abel 2151 is the one on top, slightly more, let's say, isolated from the other two. The other two clusters are Abel 2152 and 2147. Okay. So we asked for time for reserving this cluster, and we got awarded 50 hours of that time. That permits us to cover about 5 square degrees and to reach around 2 times the virial radius of this cluster. Why we chose this cluster amongst the 3? Well, this cluster is peculiar because well, the redshift of the Hercules supercluster is 0.04, so it's slightly farther away than Virgo, but still a very nearby cluster. But spectroscopic studies like this one by Irene Gulli show that the red sequence of the cluster, you can see those red dots in the color magnitude diagram, the bottom left panel here. The red sequence is very well defined down to a magnitude of about 18. And then there are very few red galaxies in the dwarf regime. The majority of the dwarf galaxies of these clusters are blue galaxies. And this is not because of spectroscopic incompleteness, because in this sample there are a lot of velocity in the red sequence, but they are not, all of these are not members of the cluster. So the general idea in the literature about this cluster is that this cluster is still information, and a cluster like this with this kind of behavior usually are found at higher redshift, like about 0.4, 0.5. So for us, this cluster was very interesting because it's a sort of a high redshift cluster that is forming now at very low redshift, so we can observe it very easily at low redshift. And on the figure on the right, I show the luminosity function taken from the same spectroscopic work, where you can see that the red luminosity function is really going down in the faint end, something that is not really expected in cluster. You expect the faint end only to be going up quite fast. Whereas if you see the one of the blue galaxy, there is of course the one in blue dash line, this is much steeper, okay? So one of the main questions was regarding these 2 topics. So the first one is to study the formation of the red sequence with particular focus in the dwarf regime. And we estimate that using the JPCAM with an exposure time, I think we chose 360 seconds per dithering, so 90 seconds per image. And the total, I don't remember which was the total, but I can check. But the idea is that we can reach an absolute magnitude in the R band that is about minus 14.5. So if I go back to this, you can see on the top of the red sequence diagram, there are absolute magnitude. This plot reaches about minus 17, so it's about 2.5 magnitude deeper. And this way we can test if with the highest completeness, of course, of the JPass spectrophotometry, we can understand if this red sequence is really information or if there is something is happening only in, let's say, intermediate regime about minus 18, minus 17. The second goal, of course, is the study of the faint end of luminosity function, where more or less the situation is the same. We can go 2-3 magnitudes deeper, depending on the final result of our observations. And so we can really see if the faint end of red galaxy is going down, or if there is some kind of an upturn that is observed somewhat sometimes in galaxy cluster. There is a sort of a part of the luminosity function with the number of galaxies going down, but then it starts going up as it is usually in galaxy clusters. And the third goal of this project is to analyze stellar mass, age, and metallicity of the dwarf population, and in particular, to understand the quenching time of galaxy, to understand if these galaxies were quenched by the environment or by preprocessing, because there were works in the literature in Fornax, I mean, very recently, in which they show that most of the dwarf galaxy, were already quenched before going into the cluster. In this case, again, we have the particularity that most of the galaxies in the dwarf regime seems to be blue, so it seems that no preprocessing happened for this galaxy. So it would be interesting to study this topic. So for this, for the future call that we are going to have, the idea is basically to extend the area of the observation, not only to Abell 2151, but to the entire region of the supercluster. And in this way, as you can see here in the map, more or less an estimation of the area that we can observe. We can include all the 3 main clusters plus these B and C overdensities that are nearby. Okay? And this will be approximately a region of 20 square degrees. I didn't do properly my job, so I didn't go playing with the observing tool yet. But more or less, it's 3 times the area that we have observed already. Why it's interesting to include these other 2 clusters in the analysis? Well, the first one is Abel 2152, so the one that is in this figure, bottom left part, is the smallest in mass of the 3. But it has a double BCG. Here I put a picture taken from this paper by Blakeslee 2001, in which you can see at the center, the central galaxy, but you can see that just on the top right, there is another galaxy that is almost as massive as the central one. So this double BCG usually is considered a sign of active life of the cluster, so the fact that the cluster is not relaxed yet. But there are other interesting things. You can see the same image on the very left, there are 2 galaxies labeled G1 and G2. These galaxies are the central galaxies of a background galaxy cluster that is located at redshift 0.13. And the galaxy of this cluster are weak lensed by the potential well of the Hercules or this Abel 2152. So this field can also be used for studying weak lensing objects. And another peculiarity is that if you look at the position where I now put the red circle, in this level of zoom, it's very difficult to see, but that is a starburst galaxy that is found at redshift 0.14. That is strong lensed by the potential of the cluster. So we have a cluster that is lensing another cluster, and behind this cluster, there is a galaxy that is also strong lensed by the central galaxy of the first one. So the situation in the sense is also 3-dimensionally very, very intense, apart from the environment of the Hercules supercluster in general. And Abel 2147, there is the one, the bottom left, let's say what is written there. You can see that it's clearly is the most massive one of the 3, but you can see it's very elongated, and there are this plot is density of galaxies. So you can see that there are 2 clear over density of galaxies. One that is the highest one in the bottom part, and one slightly on top. So again, this cluster is in a process of merging between 2 main bodies. So it's really a complex environment that is very interesting in the study of galaxy evolution in general. In this case, the central galaxy, let's say the brightest galaxy of this cluster is only 1, but the remainder of the environment is still very, very complex. Plus, we are going to include also filamentary regions. I don't know if you can see my mouse here. I don't know if you can see it. But between Abel 2151 and Abel 2147, there is a known filament connecting these 2 clusters. So we will also have galaxies that are in this transition phase between in a filament between two galaxy clusters. So basically, this is the idea on the project. I estimate that we need to observe about 150 to 200 hours. I apologize again, I didn't do the calculation properly with the new tools because this period is a bit complicated for me. We need to use OAJ bus narrowband filters. So as mentioned already by Rosa, for us it's important also we want to have the best possible photometric redshift because we want to really understand which are the members of the cluster and which are not. And I forget to mention that for the Abel 2151, we also had pilot observation with the Omega 2000 instrument at the 3.5 meter in Calar Alto. And so we cover basically with that instrument part of the region of the Abel 2151 cluster. And the goal of this is to see if adding we are serving KS band images. So if adding the KS band filter to the J-Pass narrowband filter is going to improve the quality of photometric redshift or not, maybe, but we should try. And the idea in the first project, we use exposure time on 90 seconds per image. So I'm sure that this issue about the limit of 60 seconds was already discussed in this meeting. What I checked for the images that were already observed for our project, we don't really have issues about ellipticity and other stuff for using 90 seconds per image. So we think this is reasonable. Eventually, we can discuss of reducing this to 60 seconds, but I think it's not really necessary for us. And more or less, this is all. The last thing that I want to add is that in Mame presentation before, she discussed that she is going to study the quenching of galaxies in voids, and she was interested also in studying it in different environments. So I think that these goals somewhat overlaps between our two project, and so maybe we should discuss this or in discussion session or later privately, just to say it, because if not, I'm going to forget. So, and I think that's also the connection resist up to now. I stop here.
Thank you for your presentation. Anyone have a question?
I have a comment about the limit time, because Stefano mentioned the limit is 60 seconds. Well, the recommendation is 60 seconds, although the limit is 100 seconds. And I'm happy to hear that the Stefano project, with this project which was approved in the previous call. So we have observed with 90 seconds per image, and Stefano says that is okay. So the limit of 100 seconds.
Well, I said this, Javi, because there is a table with seeing and the ellipticity of all the images that were obtained. So I trust that measurement. I didn't check by myself, but I think it's quality control by your side, and it's okay.
Yeah. Well,
okay.
But the recommendation is 60 seconds because it's the one for JPass, and then as well. If you observe in JPass mode, you are safest, no? So Alessandro said a lot of things related to observing like JPass, but we understand that that this is not valid for all the projects. So at this moment, 100 seconds is the limit. Although with time, we expect to commission at some point the guide itself. So, but
for our project, I think Javi is the same, using 60 or 90. I don't know now with the new improvements that were done, the overheads, so how much overheads I need to use 60 seconds instead of 90. This is just the difference. If I can use 60, it's better, and I will choose 60.
So next.
Okay.
Thank you. Next speaker is Jose David Balseca, and he's going to present multi-epoch observational shift for slow moving objects. Is here?
Hello?
Yep.
Yeah, could you hear me properly?
Yeah, you can share your screen.
Okay. Okay, can you see my... Okay. Good morning. I am Jose David Balseca, PhD student in planetary science at University of Alicante. My work focused on the detection of distant solar system objects using multi-epoch wide field astronomical surveys. And today I'll present MOS, multi-epoch observational search for slow-moving objects in the other solar system. So first, I will first give a brief scientific context about the distant other solar system. Then I will explain why the multi-epoch observation is especially useful for detecting very distant objects. So for several decades, Pluto was the only known trans-Neptunian object, and the region beyond Neptune remained almost unexplored. Pluto was discovered in 1930, and soon after, Frederick Leonard suggested that Pluto was suggests that it might not be an isolated body, but part of a larger distant population. Later, Edgeworth and Kuiper proposed the existence of this like reservoir of icy bodies beyond Neptune. This region is now commonly known as a Kuiper belt, or more precisely, the Edgeworth Kuiper belt. In parallel, Jan Orr proposed the existence of a distant spherical reservoir of cometary bodies surrounding the solar system, now known as the Oort cloud. A very important theoretical step came in 1980 when Julio Fernandez proposed that the Trans-Neptunian comet belt could be the source of the short period comets. This was important because it gave the Trans-Neptunian region a dynamical role. It was not only a hypothetical population beyond Neptune, but a possible source of observable cometary bodies. And the observational breakthrough came in 1992 with the discovery of 1992 QB1, the first Trans-Neptunian object discovered after Pluto. Since then, dedicated surveys such as the CFHT also have revealed many different Trans-Neptunian populations. However, the distance of the solar system are still far from complete, especially at very large heliocentric distance. This leads to the main motivation of the project. Could large distant bodies still remain undiscovered? So the motivation come from the early evolution of the solar system in the framework of planetary migration models. The NICE model, the giant planets did not remain exactly where they formed. This planetary migration, especially the migration of Neptune, strongly affect the primordial Trans-Neptunian disk. Dynamical models suggest that this primordial disk that was much more massive than the current Kuiper belt, with order of 10 of Earth masses. And then with this migration of Neptune, the disk was dynamical excited and many objects were scattered. Some objects were implanted into the current Trans-Neptunian region. Some were sent to distant orbits, and many of them were removed from the solar system. In particular, this grand immigration model suggests that the primordial disk may have contained thousands of Pluto-class bodies. Most of these bodies would have been scattered away during the planet migration. This is important because the current Trans-Neptunian population may only be a small remnant of a much larger primordial population. So these works that are relevant because they combine dynamical and collisional evolution and trying to reproduce the observed properties of the current Trans-Neptunian population and fit well with the observables. And this work dedicated for the searching of such objects. So the key of this point is even there is a small fraction of these large primordial bodies, some Pluto size or dwarf planet size objects could still remain undiscovered beyond 100 astronomical units. This is just a figure where I show the apparent magnitude of distant objects as a function of heliocentric distance, where I use the most popular surveys nowadays, and I compare the apparent limiting magnitude versus the heliocentric distance. In this way, it's possible to have a point of view of the limit of magnitude for each survey and which could be the best to detect these distant objects. For the largest objects such as Pluto, Mercury, and Mars, I use a higher albedo range between 0.5 and 0.9, consistent with the brighter surface expected for large icy bodies. The horizontal lines indicate the approximate magnitude of different surveys. But the limiting magnitude is not the only important factor, but also the multi-epoch strategy. Why? Because these objects, well, as I show in the previous figure, detecting distant objects requires enough depth. However, this is not enough because the objects beyond 100 astronomical units also show an extremely slow apparent motion. In a single night, this displacement can be almost negligible, so may look like stationary sources or be confused with stars or other. So this is why a multi-epoch strategy is essential. Instead of relying only on a single night motion, we try to compare detection across different nights and look for a small but coherent shift over time. The map over here is the Catalina Sky Survey choose in my thesis because of this strategy, a multi-epoch strategy, and with a good balance between a multi-epoch and a limiting of magnitude. And the strategy, okay, in this slide is I want to show the search strategy in a progressive filtering process. So the idea is we start from a large number of the text sources in the images. Most of them are not objects we are looking for. Many are static sources such as stars and galaxies, other spurious detection, cosmic ray. So in the algorithm I am using my thesis, remove these sources step by step. So the idea is to remove first the static sources using the different images of different nights, and then filter these spurious sources, the objects like asteroids, discard known TNOs because we are looking for new objects. And finally, the remaining unknown candidates, we try to link detections across different nights in a fit preliminary orbits. If the detections are dynamical consistent, the candidate may become a potential new solar system object. So why MOS? Because after testing the method I showed you previously with Catalina Sky Survey, the next step is to use is to move from to using a dedicated observing program. This is the idea behind MOS, the multi-epoch outer solar system survey. The goal is to use the JST250 to repeat or select regions of the sky with a strategy specifically designed for distant objects. Catalina Sky Survey was useful, but it was not enough because it was not designed for distant objects. This is why with MOS we could keep the multi-epoch advantage, and in addition it combined the elements need for slow objects detection, repeat observation, and deep magnitudes to reach faint objects. In this slide, I summarize the feasibility of MOS. The baseline strategy is to obtain 4 100-second exposure per field. By stacking them, we gain about 0.7 magnitudes, increasing the distant range where the larger distant objects could be detected. The current plan is around 100 hours per year over 3 years, covering approximately plus or minus 5 degrees around the ecliptic plane. However, with a longer program, the explore region could potentially be extended up to plus or minus 12 or even 30.5 degrees. We are still evaluating the optimal trade-off between reaching a limiting magnitude close to 25. We are also considering the observing mode, including broadband filters or unfiltered observations. Since unfiltered observation might degrade the quality of the image, one possibility is to use 2x2 binding to improve the signal to noise ratio and make the data more robust. So finally, using around 6 visits on different nights would help compensate the weather gaps and still provide enough epochs for candidate linking. And this figure follows the same idea of the previous plot. The idea is to show the detectability when I present the same, the apparent magnitude versus the central distance, but in this case for the GST for different configurations in one single exposure, and if we do a stacking of four images. As you can see, I compare two observer modes. And the main point is that stacking for exposures gives a gain of about 0.75 magnitude compared with a single exposure. So this plot illustrates the balance behind MOS using repeat exposures to gain deep through stacking, while keeping the multi-epoch structure needs to identify slow motion objects. In this figure shows the projection in the all sky mole weight in equatorial coordinates. The black line represents the ecliptic plane, while the red dashes line show the region within plus or minus 5 degrees on ecliptic latitude. I also include the galactic plane, and because of the crowded stellar regions can make the detection of faint moving objects more difficult. Okay, this is the blue shadow region represent the simulated survey fields distributed around this ecliptic band, and the color cycles correspond to the known objects recovered in the Catalina Sky Survey with my pipeline, including Sedna, Eris, Sarasia, Orcus, and others. And these stars indicate two new objects discovered with my pipeline applying the Catalina Sky Survey, the Plutino 2020 TZ 114 and the Centaur 2022 BO71. The main point is that the Catalina analysis validates the method. It can recover no distant objects and also identify new solar system bodies. In this sense, Catalina acts as a pine finder for MOS. And to conclude, MOS is proposed as a dedicated multi-epoch survey for the distant objects. It builds on a detection strategy already tested with Catalina, where we recover no distant objects, identify the new solar system bodies. The main step forward is that MOS would transform this archival proof of concept into a systematic survey using a homogeneous GST data set designed from the beginning for slow moving object detection. Beyond possible discoveries, MOS would also provide a valuable legacy dataset for future research and for small body science in general. In this sense, MOS would strengthen the role of GST and GBCAM in the exploration of the distant outer solar system. Thank you.
Anyone have any question? I have two questions. So I understand from your presentation that you could observe in non-photometric conditions, I guess.
Say again?
What I understand is that you could observe in non-photometric conditions, which means that you just care about the position of the objects, not the flux you measure.
Mm-hmm.
So I would recommend you to ask for non-photometric conditions. And when the call for proposals is open, you should ask, I guess, for non-photometric conditions. And the other question I have, no, I forgot. So, sorry. Can you turn back? Yes, sorry. Now I remember. So, and about the observing without filter, sorry. About that, the problem is the flat field correction. But again, if you don't care about the flux, the absolute flux, I guess you don't care about the flat field correction, because observing without filter affects this flat field correction, but especially if you choose the 2x2 binning. If you choose the 2x2 binning in broadband or in unfiltered observations, is a non-standard, and then what means is that the flat field correction may be impossible. Just for you to know more.
I would discuss that. I just wanted to comment on that because I would say that it's not impossible to observe in binning 2x2 with no filter in terms of the reduction. So this it would require a new platform. That's true. But I wouldn't discard just since the beginning. So I want to say the condition is that you need to have flat fields, but besides that, I guess that is consideration.
Yeah, but at the moment, what we do, we observe some flat fields without filter, but it's like the less priority flat field, and so we have less, no? But I don't know if they are enough or.
C is personal.
Okay.
So, and the other, well, but I'm glad that you are planning to observe not on I mean, avoiding the plane of the galaxy, for sure benefit your project. But maybe you mentioned it, but it was not clear to me. So, what is the regions where do you plan to observe in your diagram? Can you that?
What is the region I hadn't planned to
make the observations? Yeah.
The idea is to observe close to the ecliptic plane because most of the known trans-Neptunian objects are distributed in this region, and so it's likely that if there are some new objects, should be here in this.
Yeah, but the whole band.
Of course, avoiding the place of the galactic plane.
Well, my question was if you in a specific area within that band, because I understand that the whole band, even if you don't observe the plane, is very large.
3,600 degrees.
So that was my question. Okay, thanks.
So, can I, if you want, I'm happy to share some of the Aurora fields so that you can see, you can test your project. But you have to come to the well to get them. There is some jamón. Because it's
Wait. No? Hey, can you repeat the question, please?
So, what's an invitation? So, if you want, can you hear me?
Yes.
All right. It feels like the Pope. So, I'm happy to share some of the Aurora fields so that you can test your method on some unfiltered JST data. And but since it's a lot of data, I suggest either you come to Teruel and get some jamón, or I come to Alicante and you invite me for some rice. I like the second option.
Thank you so much, of course. The second option.
Pensamos del arroz y ya te decimos.
So, someone else, any question?
An uncomfortable one. What about the moon conditions that you need? Do you think this could be run with the moon over the horizon, or that would impact too much your project? I don't know if you hear me.
No, you have to speak right in there.
Okay. So my question was about the moon conditions. It is critical for you to have dark skies, or it is possible to conduct this project with some sky brightness from the moon?
We are aware that the conditions are worse with gray nights. So we prefer the dark.
Everybody's got.
I should try. I must try. Thanks.
Okay. So thank you for your presentation. Next speaker is Tony Santana Ross. He's going to present Tori.
Yeah, hello. Can you see my screen now?
Yep.
Good. Let's put it in presenting mode. So thanks a lot for the invitation, for allowing me to present the idea for this survey. And sorry for not being there. So it has been a difficult week and I could not travel. So I prepare a very brief presentation just to give a first glance of what we have been done and what we plan to do. And then we can maybe discuss a bit, or you can let me know if this makes sense for the scope. So first, to give you some background, what we aim to do here is to discover objects which are very close to the sun, and we call them inner Earth objects because they orbit is constrained inside the orbit of the Earth. Also, you can see them referred as Atiras because Atira is the name of the first asteroid that was discovered with such an orbit. And as you can imagine, because of the limitations to observe close to the sun, our knowledge of this population is very limited and strongly biased. We currently know 38 Atiras or interior objects, and most of them are quite large, meaning more than 1 kilometer size. We know very little about their physical characterization, so it's something that has to be done in parallel to the survey. So apart from discovering new objects, what we aim is to characterize the known population, and maybe also if the newly discovered objects for some reason have some interesting orbital characteristics, then they can be a good also target for characterization. And why do we care about these objects? Well, there are two main reasons for that. One is that they provide constraints on the solar system formation models. And since we know very little about them, every single object discovered is adding new constraints. And also because of planetary defense. And then I'm showing this graph here from ESA, which if you see on the right, you see the number of objects that have been discovered with more than 1 kilometer size. This is the statistics for the whole NEO population, not only for interior objects, but the whole NEO population. And you see that we are almost complete here. We think that most of the objects larger than 1 kilometer have been discovered already. But if you look at the next, let's say, range of sizes, which is between 300 meters and 1,000 meter, there is still a lot to be discovered. So we think that more than 1,000 objects are in this range, size range, and have not been discovered yet. And you can imagine that these kind of objects can be hazard for the Earth. And we think that the reason we have not discovered them is mostly because they are in the sun direction, and that they are escaping from the regular surveys. So that's why we think that if we focus on interior objects, we can contribute in discovering this kind of objects. So we help with planetary defense. So this is a paper, a figure from a paper that we did in 2022. Basically, we use Blanco telescope with the NECAM survey to look for interior objects. And so this is basically a similar thing that we plan to do with GST, but in the southern hemisphere. And in this sphere here, we show the semi-major axis of all known NEOs and also the known interior objects, which are plotted in red, and also the inclination of their orbits. So you see that we are really in the border, in the limit of our knowledge here. So each one of the newly discovered interior objects are really in the limit. And we think that there might be much more objects in smaller semi-major axes, but we have not discovering yet, not because they are not there, but because of the limitation of the current surveys. So basically, if you want to observe these objects or you want to discover these objects, this is just a pure plot that I generated. So imagine that you are an observer in the Earth, and if you want to point to orbits that are inner to the orbit of the Earth, of course, you cannot directly point towards the sun, but you instead need to observe with a certain angle. And this means basically observing at solar elongations between 35 degrees and 45 degrees. So this is the optimal range. And by pointing at, of course, to point at these directions, the only moment of the night that you can do that is during the twilight, because otherwise, in the middle of the night, you will be pointing your telescope out or on the other direction. So in the only moment that you can do that is during twilights. Of course, apart from that, you need to point very low because you need to start observing as soon as the sun is low enough, and you need to point as close as possible to the sun. So you need to observe very low, meaning that you are observing always at high air mass. And also, you had to account with a very nasty effect, which is that the background signal during the time of your observations can dramatically change, and this sometimes make it difficult to process the images, and this has to be considered when creating your pipeline. So in short, what do you need, or what are the requirements that that you need to have a successful survey with this goal? So the first one is critical. So you need a telescope that is able to observe low, and low meaning in the range of 15-20 degrees elevation. So if your telescope cannot point below 20 degrees, then probably you're out of business. Then also, of course, the telescope aperture is important, because the larger it is, then the smaller objects you will be able to find. So I mentioned these 1 kilometer size objects. So basically, if you have a 1 meter telescope observing during half an hour, more or less, which is the twilight time, you can aim to detect objects which are above this 1 kilometer size. But if you are willing to detect smaller objects, you definitely need larger apertures, and 2.5 meters is quite ideal for that. Of course, the field of view is important, because the larger the field of view, then the higher probability you have to discover an object, and a 3 square degrees is more than enough for that. We are currently using a smaller field of views with other telescopes, and yeah, and the GST provides a very nice feature here. Then the other thing is the camera readout time, and the reason is because since you can only observe during this half an hour or 40 minutes, and it's the only moment that your field is visible, you want to have as much as as much photons as possible during this half an hour. So if you have long readout times, you're losing time, so it's not optimal for that. So the idea is to use strategies, for instance, using binning and cameras that provides the fastest possible readout, so that you reduce, or you make this time, you take the most of profit of this time. And then the last thing to explore is filters, and this is related to this background thing that I mentioned. So using filters can help you cutting these effects, but is not required or critical. I mean, we can use that with software as well. We have some tricks for that. And what I learned from the presentations is that maybe for GST, the best idea for us is to go unfiltered, but this can be discussed. So this is a comparison with similar surveys or other surveys that are aiming to discover news. And just to put a bit of a context, that GST provides a very competitive and very good conditions for this kind of survey. So basically, you want, as I said, at least a 1 meter telescope, and you need elevation limits that are at least 20 degrees, but it's better if you can go lower in this sense. With some private communications with the operators of GST, you have done some tests, and you can push as down as 15 degrees. This is what I understood, and this is very nice, and making the telescope very interesting for that. And also the field of view, it's 3 square degrees, so it qualifies here with the other surveys. The other thing interesting here is that I don't know any other telescope in the northern hemisphere that can provide these numbers. So in this sense, it also opens a new possibilities here, because we have been using Blanco, but this is in the southern hemisphere, so we are not competing with Blanco in that sense directly. And also the elevation limit, as I said, we can, by gaining this 5 degrees elevation limit difference, it means that we can point even closer to the sun, and we can detect even objects with even a smaller semi-major axis. Of course, as I comment, other surveys like Gaia or the space-based surveys are not playing a role here because they avoid the sun and they can never point at that direction. So we cannot use them for detection of these objects. So just very briefly, we have developed a pipeline to plan the optimal fields to be observed. So basically, it's a Python script which it takes into account the elevation limits of the telescope, some limits on the ecliptic longitude and latitudes of the field that we want to observe, the maximum duration of the observation and the elevation of the sun, and then it provides you the optimal fields for a given date, and this is what we use really to plan our survey in other telescopes. So then once we get the images, what we do is we process them with a system which is a synthetic tracking technique. For those of you that have not listened or heard this term in the past, what it basically does is that you get the images, you stack them, but you don't stack them just serially, but you stack them in the direction of the asteroid. But of course, if you are aiming to discover a new asteroid, you don't know the direction of the asteroid, you don't know the rate of the asteroid. So what the technique does is it creates millions of possible orbit solutions, and it stacks your images in different directions. And this allows you to discover objects that cannot be visible in a single image, but instead, you once you stack the images, you get to see the object, and this, of course, increases or improves the limiting magnitude of your survey. So we introduce that in our pipeline. And basically, what we aim to do is to follow fields that are between 15 and 25 degrees of elevation during the twilight time. We limit the exposure time to 30 seconds, and then there are at least two reasons for that. One is to reduce the background and to reduce the possible saturation of the background when observing really close to the sun. And the other one is because the rate of the objects that we aim to discover usually move in a way that if we observe more than 30 seconds, then they start trailing. So then you're not really gaining anything in observing longer than that, but instead you're losing a signal from the object. So more or less the optimal exposure time is limited between 20 and 30 seconds. And then we stack all the images with this synthetic tracking technique that I mentioned before. Then, as I said, we can go with unfiltered images. This is not an issue, and we can deal with that. We suggest binning because then we reduce the readout time and it is not critical for the kind of objects that we are trying to detect. And we aim to request 30 hours per semester, and this is important. It's bright time only because we are using twilight time, so we are not competing with most of the surveys that have been presented. So, well, with this survey, we expect to push on the detection of these objects that are really tricky and not covered by regular surveys. So we really need a dedicated survey for that. We aim to reach completeness for the 1 kilometer size objects above, let's say, a semi-major axis of 0.6. And in parallel, we also work on physical characterization of the objects being discovered. And for that, we are using additional telescopes. Usually we use Gemini SOAR or even a smaller one like the Joan Huro telescope, which is a 80 centimeter telescope, but it can really point as low as 5 degrees elevation. So it it's very convenient for this kind of survey or this kind of characterization, sorry. So basically that's what I wanted to present. And now I'm open for discussion or questions. I cannot hear you. I don't know if there are any questions.
Question? I have one question. You said I read in the presentation that you were going or you would like to use unfiltered images. Wouldn't it be like the opposite? I mean, if you're observing in bright time with unfiltered images, you will get a lot of noise in the background. How would you manage with that?
Yeah, that's right. I mean, ideally, what we are using, the telescopes is we are using an R filter in order to cut this background. But maybe I misunderstand it because I could not follow yesterday's session, but I understood that it's a bit tricky to use the filters with GST. So that's why I said that unfiltered it's also a solution. I mean, it's also fine for us because then we use some synthetic flat fielding and some processing of the images, and with that we reduce these background effects, and we can also detect the sources. So it's something that we can deal afterwards with processing of the images. So ideally, in short, of course, our filter is the best solution for us. But if it is not available, unfiltered is also fine because we can deal with that.
Yes, you should. Is the talk from yesterday recorded, Juan and Antonio?
Yep.
Okay, so we will share the I guess the YouTube link to all of you.
That would be great, yeah.
So in principle, to observe with the broadband filters is that there is no issue. Is the same. In fact, it's the same. The strategy, the observational strategy, the pointings are the same as unfiltered. So it's not that difficult. Would it be possible to observe also with IBAN, for example?
IBAN sometimes it's okay. It's a bit tricky, but we could try. I mean, the best thing we could do is to do some tests and see how it works. Maybe for a known Atira and see how it works. Yeah.
Yeah. Well, the reason is because the IBAN filter tray is going to be installed always or almost always, and the R band, if installed, it will be on a specific time periods.
Okay, so then definitely IBAN maybe can be a good solution, and the best we can do is do a test, perform a test with unfiltered and IBAN and see what it works best for this case. Yeah.
You can always, all of you can always ask a DDT. DDT time, the discretionary director time is always open, 50, just in case you want to do a test before your proposal. Of course, now we are in a very limited time period, but well, you should know, all of you, that the DDT is open for test if you. Okay.
That's a good idea.
Let me get closer. So, one comment and a question. The comment is any project called Torico should get time by default. Can you expand a little bit on how you plan to do the flat fielding? Because since you're observing you observe when we do the flat fields. So
we usually what we do in this case, I mean, not only in these cases, generally what it works best for this kind of survey is to use synthetic flat fielding. So what we do is we use littering, and then using the same images, we create a pseudo flat, and we apply this pseudo flat to our images, and then the critical point here is, as I said, the background change during the duration of the observation. So this is making it a bit more difficult. So sometimes it's even better to create different pseudo flats. So create 3 or 4 pseudo flats, and then use them, apply them to the different moments of the duration of the sequence. And by doing that, we could get quite good correlation for other telescopes. So I think that this should work for this one as well.
I'm glad I'm not the head of the data department. Thanks.
No one else? All right. Thank you again.
Thank you.
John? Now is discussion. Okay, so well. Okay, well, first of all, let's thank you all of the organizers and the ones that are with the green. We have done it well. Remember that you should put these plastics on the table before leaving, please. And now we will have a small session for discussion. I have some points prepared, but feel free to talk about what you feel is important to sum up the meeting. So remember that the goal for us, I'm going to sit down just to open this, and then I will stand up. Remember that the goal for us is especially that, we will open the call for proposals in July. And the goal is that, that you submit very good proposals as the ideas we have listened during these 2 days. But also, for me, or for us, for the observatory, it's important that 0 proposals get rejected because of technical reasons. Last time, there were a few proposals that were rejected for technical reasons because they were not feasible, and for us I guess that the first time it shouldn't be normal, but at the end, it can be expected. But it's important that 0 proposals get rejected because of technical reasons. So this is the main goal. So the main point is I want you to leave from this meeting is that please, if you have doubts, ask us in order to be sure that what you are asking for is feasible. We have recorded the talks from yesterday and today, so that you can go and watch my talk 10 times if you want, or ask me. I mean, you can watch it once, and then if something is not clear, please come and ask me, because I will feel very bad if just one proposal it gets rejected for technical reasons, especially for those that are here remote or in person. Well, things that I have seen that we could discuss is, there could be synergies between groups, and for this also, some people has asked me, and then, I guess that the synergies sometimes is not possible, but in order to help this, I guess that we could allow 2 PIs in the proposals. I guess this is somehow already allowed, no, Hector, in the system is allowed to have a PI and a co-PI, but because now in this open call for proposals, we will use the template. We could include two PIs at the same level. I don't think why not, and especially to help the synergies between groups. Again, this is not mandatory. You don't need to do it, but if you feel that you can. No, I mean, we have listened a lot today about galaxy clusters, the ultraviolet part of the spectrum. Also, I have listened the Hercules supercluster in two talks, but I guess that synergies would be make your proposal stronger. Also, two proposals about the galactic anticenter. Again, it's not mandatory, but from my point of view, allowing two BIs, for example, it would help. So no one feels that is losing the leading of the lead part of the proposal. Also, I have listened today out observing inside the JPass footprint, especially in the ET field, and in fact, it was Juan, no, not you. The other Juan. Sorry. He asked if the ET field part, which is covered by JPass, would it be covered in 2028? So I have seen that probably not with the current plan. So with the current plan and the current strategy of JPass in 2028, this part is not going to be covered. Don't count on that. Although in JPass there is this collaboration board, the survey meeting committee. There are several committees. If you convince all of them, maybe we could change and go there. It's difficult, but so in principle, with the current plan, don't count of reaching that area of the ET field. But okay. Now, do you have some points that you would like to consider before continuing my points? Because then I can have like an idea of the time we have. Anybody would like to comment before? If not, I have plenty of time to discuss all of this.
Mamen raised.
Okay.
Just one question.
Okay.
If you, regarding the data processing, you may be surprised that I'm addressing this topic. Just to, it would be helpful if you can stress if you need any non-standard or non-default programs of the data processing. I mean, I'm referring to whether you need quality images, whether you are interested in this homogenization of the automatic calibration. Basically, that are the 2 points that I would appreciate if you can express or say something about your needs.
But here, yeah, I mean, in this.
Not necessarily here, but whenever you make the proposal to at some point to have this.
Okay. Okay, so but you can comment it here or send us your this request that Hector is saying. And Mamen?
Yeah, I have a question about the times. So in the use of the bright time, if your estimations are really like you need too much time, so it's unfeasible some way, do you still need to put some estimation for bright time, or it's okay to don't have it?
I don't fully understand the question. Can you repeat?
Yeah, in the case of the bright time, if bright time is unfeasible for the project because the times that are estimated are like too much time, do you still have to put a percentage of bright time for your project, or it's okay just to don't put it?
Okay, no. This is the I guess that the common thing for the easiest thing to think is that no, you ask the time you want. You can ask all of your project for dark time. Or gray time or bright the time or the type of time that your project needs. So you don't need to ask for bright time. The percentages is just for you to know the available time and also for you to be realistic. In fact, well, this is the next point that I would like to talk about. But before going there, because it's important, I would like to know if there are some more points, as Hector said. online? Is there? No? Okay. So then I would talk. Yes. Yes.
You specify the time, the maximum time to project, but how much time you actually plan maximum time you plan to approve for all projects? How many projects you expect?
Okay. Well, let's go to the time because I would like to be to be clear and I would like to help you to be realistic. Well, the total time is I'm going to sit down. The total time is 1,200, and this is approximately. No, this is based on the statistics on the past, and then also not only weather but also technical losses. So more or less, we will have 1,200 hours in total. But these hours during the 5 years are for all kinds of conditions, sky conditions. So we cannot know how many projects we will approve. This depends on the different projects asked. No? Maybe one project asks for all the time and it gets it. I doubt it because at the end, it's not. Well, this is my view, and I don't decide which projects are approved. So I'm going to close this because if not, I'm going to get distracted.
So one question from the projects that let's say you have so far. Yeah, but I mean, what is the time requested? Is dispersion?
Yeah. Well, there is a big dispersion, but for me, it's too much. So that's all of the projects has asked too much time. I guess that it's normal, and I could understand why. So this is. I don't want you to get the idea that you should ask less or. No, I want you for your projects to be successful, but also to be realistic. So I don't know how many projects. At the end, I guess there will be a few because it's very risky, I guess, to just, for example, even if there is one project that asks for all the time, it's very risky maybe to approve one project. I doubt that the committee, which is here, some of the members are here, they are free of course, they are free to approve the project or the projects they want, but it's very risky to approve one project. So at the end, we will have a few. But I don't know how many. In the T80 we have 4, so I guess that it will be a similar number. Maybe 3, maybe 6. We don't know.
But 1,200 hours is the maximum for all projects.
Yes.
It could be 1, it could be more.
Yes, but it should be even much less. Why? Because what much less because what I have seen here is that the people want, for example, dark and photometric time. So then. And that's dark gray. No, let's be more, not be too. Let's be more flexible. For example, if you consider the sky conditions, at the end we will have 240 hours more or less during 5 years, which 240 hours per year during 5 years. This means that from these hours to 120 will be dark, 60 hours gray, and 60 bright. And more or less, that's the reason I put here this symbol is 60% of this time will be photometric. A very big uncertainty there. So be realistic. Don't because then per year, then in fact after this, I should put this later. So be realistic, and something I like a lot about today's talk of Luis. Luis, for example, you mentioned 2 strategies, and in fact, what I recommend is all of you to put, well, at least 2 strategies. 2 strategies in area, not in area, are even the 2 strategies for me.
they were very exigent. In fact, they would put even less because for example, if at the end 3 months of observations corresponds on average to 27 hours in dark, gray, and photometric time in total in these 3 months. So if your field is observable within 3 months, don't ask for more. So in 5 years, this means that you could ask 135 hours in total. Of course, you can ask a bit more, but please also send the strategy, the realistic or the less exigent strategy. Of course, also, well, one thing for you to know, this is my idea also, is my field observable or not? I think if your object is observable above 40 degrees of elevation, more than 2 hours or more, you can consider this period of time observable. So this is very important. Of course, this is not exact, but more or less. And I wouldn't observe below 40 degrees of elevation any field. Because the optical quality decreases a lot below, starts to decrease below 40 degrees, especially if you ask for 100 seconds exposure time. With 60 seconds, it's also decreased, but it's not that much. So, if you want to know how many months your object or field is observable, check when or during which months your object is above 40 degrees of elevation during at least 2 hours. And then you have the months, it's observable, and then you can check how much time is realistic. And here I put what are the consequences. You can ask also for all of the time available dark or for all the months, but then if you ask for the time for more time that is available per month, then you will compete with all the projects in all the coordinates, sorry, in all the position on the sky. But if you ask for the time available per month, you will compete with the project asking for the same right assertion. So it will be easy. So I don't want for you to think that you cannot ask for all. Yes, but the competition will be stronger. So then you can ask for all, but then also put the second strategy, as for example Luis has presented today. I think this is very useful for us and for the CAT. And also, of course, put what are the scientific goals that you can reach with the second strategy. Maybe they are not all, but maybe they are not. So then the CAT can also the committee can decide better based on the different strategies. This is a recommendation. It's useful for us, for the committee, and also for you. Questions about this? About the time?
And that you offer also includes not for the rigid time.
Yes.
One more crazy question. And you are asking about specific fields to be observed. But what if field is not fixed, but it evolves through the year? Can it be provided like a list of fields for each night, which should be actually observed, and depending which night is observed, different field?
Yeah, well, this is a very good question, Boyan, and you are not the only one considering or asking about, well, I don't care about, or I don't care, no. I don't have a specific coordinate, no, but I can observe during the whole year. Then this changes the philosophy, and you can ask for all the time, or for all the time. And then what I would do at this moment is you cannot specify the coordinates, and it's not needed. So you just say, well, although I don't have if your proposal is like this, that you don't have all your coordinates, depends on the night, or even the time, the minute, the second, then this will be decided in a later phase. So ask for the time and the pointings. For example, do the estimation for one night, or one pointing at some point, and how many pointings at the end you will have. And we will work during the legacy definition, the legacy survey definition. We will work on defining the coordinates in as a function of the day, of the specific time and date. I don't know if I'm answering.
Yeah, more or less, yeah. But that would mean that, for instance, it can be observed at any time when there is a free slot.
Yes.
That is, from my point of view, that's flexible.
Yes, of course. We don't give nights. We don't deliver nights. We deliver observing blocks, and then typically it's 1 hour, no more than 1 hour, except if you are called David Morate. I don't know if it's yeah. Then you can ask for more. But I mean, always we are flexible. No, the ideal case is to have observing blocks no longer than 1 hour because the conditions change. But if the project requires to be longer, so then we can manage to do that. But what we deliver is free slots made of more or less 1 hour.
Maybe another way to put what you mentioned before is like considering your project at some point, also assess what is the minimum amount of data that you need to reach some of the goals of the project. I guess this is something that we already asked for some time in general, but again, in the same line of the previous comment,
yeah,
I guess it will help the committee to assess it.
In a similar direction. So in T80 now there are the legacy projects, the DDTs, and the TOs. Are there going to be TOs for T250?
In principle, there should be at some moment, but I think we are not ready. So at the moment there are not, and I don't know when. Okay. This depends on the priorities we give to the to the developments, different developments we need. No, for example, yes. Well, there are a lot of things still to do, no, like auto guiding or TOs or other things we need to do. And I think we are still not ready to give a quick response with the kit.
Thanks.
But again, this is I guess that this is the same as for me. It's clear that we need to commission the guide sensors. It's clear. No? So, but if you feel like we need to give the opportunity of observing target of opportunities, also say it, and then because a lot of you have said, well, I want to observe more time. So for me, it's clear that this necessity is strong, but the same for the target of opportunity. Pressure us, and then we will prioritize different things as we can. Okay. Well, other thing I would like to stress is that the pointings given by the hub are not mandatory. You can plan your own pointings, although it is recommended because for me it's easy to use it. But you can plan your pointings. You can find a better strategy. For example, also from Luis' talk today, I have seen that you have a circle. Well, it was not a square, no, the pointing the area you want. So please feel free to plan your pointings to maximize the area you are interested. This is just a tool to make some of almost all of the projects easier to plan. But I understand that it's not. We understand that this is not always the case. Maybe it's for almost all of you, but it may not be for all of you. So it is recommended because we think it works. It's maximized, but maybe it doesn't work for you. And then the filler. Okay, now today that we have listened more talks, now I have seen that different projects can ask for filler time.
and consider asking for bright time and or non-photometric time. So I put here the numbers. So it's 96 hours per year are more or less are non-photometric, and 60 hours per year are bright. The 60 hours bright contains some of the non-photometric and also the same. So you cannot sum these two numbers. So I guess, yes, for example, the most survey can be done by, I think, in not ideal conditions, in non-photometric ones, probably not during bright time. I guess that not, because also the moon at some moment will be very close for some of the observations, but non-photometric time, I don't see why not. Also the JFast or PhotoFast project can also be done at least partially in filler conditions. So please ask for them, and the pressure is not as high as in photometric conditions and dark time, which is the zone where I would be very happy to give all of you the time, but there is not enough time. So it's impossible to observe all of the projects that we have listened. So, but for the filler, yes, yes, Tony. I think you. Okay. Well, Tony, were you here in the beginning of this discussion? Well, here it's important maybe for you to agree. So I have seen synergies between different groups. So to help to find synergies, which is not mandatory to ask or to join projects, but in order to help the people to join projects, I guess that allowing 2 PIs helps that. No, I guess you agree, or
I think that if there, I think that some synergies are apparent, no? Or we all thought about some synergies between the different projects that we saw yesterday and today. So if there are projects that can actually share, I mean, the observational strategy, the pointing or the area of the sky that can be observed, at the end, joining force will result in a stronger and a more powerful proposal. So, of course, it is not mandatory. Every PI and research group, in my opinion, is free to present the proposal that they think they want. But in my opinion, this is a piece of advice. So you can join force. Working together makes a stronger group, stronger proposal, and hence increases the possibilities of being able to time. So I can think out at least one example from today's presentation, but this is just an idea to think about. Of course, this is entirely open for the different PIs. But I think that it could end up in a more powerful, more robust proposal benefit.
But do you think can we allow 2 PIs at the same level?
2 PIs in the same.
Yes.
Why not?
Why not?
Why not?
Why not? Well, I don't know. Or 10, I don't know. I don't know. Yes.
I mean, imagine 3 projects that are, I mean, in principle different projects, but they share the data. What's the problem?
For me, no, but I don't know. Maybe.
This is a formality, right?
Well, but at the end, it's important for the people also to, I guess.
Yeah,
I don't know.
I don't see why not to allow that the project comes with 2 PIs or 2 co-PIs.
Okay.
I don't see why.
As long as there's at least one.
Can be 3 projects sharing observations as well. That's a problem for us, no? We present a project, whether a project or
Yeah, for me,
that's a problem. I mean, I don't know what's easier, but
in principle, there is no problem, but I don't know, maybe.
I cannot think, I mean, I don't see why not. I see the benefits, I don't see the problem. Right
But
now,
people, I mean, like, if people want to lead a project that have a name and things like that, because it's important for some people, especially for young people, they can always be 3 projects in observation. And they make when they present it in the talk, something like that, different project and it's different from the other. If that's a problem for people, I mean, for me, it doesn't matter one way or the other. But I know that some young people are going to be. Yeah.
Well,
No?
but for that, in my opinion, we should allow 2 or more PIs. Then because
if this is my personal opinion, we discussed that before, but if that helps the teams to present more powerful proposals, more robust and well-defined proposals, I think this is a very important piece of information to take into account. So if the observatory tools are not allowing now to have 2 PIs or even 3 PIs, this is something that we can modify, because at the end what we want to have is the best proposals possible to get the maximum out of the data that the observatory is producing. So I don't think in a reason why 2 PIs shouldn't be allowed.
But in this case, because it's a document, it's a template document, it's possible. So we are more free that we are not using.
I know it is possible.
So now, okay.
I mean, the following door, the proposal gets stronger because there are more certificates in the proposal. It's not because, I mean, by joining them, you will make a unique case. No, that's it. It's very important because if you try to make a unique case, you in a way you probably increase the requirements of every single, let's say, project, and then you are rather than improving, you are lowering the quality. So the strength is in having more certificates.
Sharing there is a larger research team behind the proposal with a larger a large number of expertise. So yeah, you increase the research team, the science basis, and at the end, the scientific outcome, the same set of data. So I think that makes the proposal much more stronger. Yeah. And if, as a result of the discussion between the different teams to elaborate the science case, I mean, you may have an idea that you didn't think before because you are sharing expertise, you are adding to the team. But yeah, I meant that there will be a larger and stronger team behind the proposal with more scientific cases to be covered. I think it's a win-win.
Yeah, well, this is something I have talked with some of the participants, and I think this at least it will help to try to find synergies, no, between different groups. But again, it's not mandatory.
There's nothing mandatory. The guys can do whatever they want. We're just offering what we can offer. Opening, I mean, we are completely open to new ideas.
The only thing is that for defining the theme, for example, if we were to explore the already observed feeds, give us a survey, maybe the quality, not the to some extent, I mean, we probably need a strong debate from your side.
We are, I mean, Javier has mentioned several times, but if there is anything that here from the observatory and here from FECA that we can do to support the preparation of your proposals, it is our top interest to help the BIs and the teams to prepare the best proposals possible. So do not hesitate contacting us if you have any question, either technical or from the management point of view, or even strategical. I don't know how to help from this last one, but yeah, we are here to support you, support the PIs to prepare the proposal. So do not hesitate contacting us.
But about the fields, Alexander, you are asking about the fields, to choose the field, and you don't want to or you wouldn't want to propose to observe a field that is going to be observed soon with JPass, or what is your question?
No. I mean, the point is that you want to get deeper, right? I think that we presented today a number of projects that require, let's say, as deeper as better.
Yeah.
So the point is that if there are already observations, in principle, look like an advantage, but then we should care about whether these observations are all useful. For example, they are photometric or
well, JPass observations are photometric, for example. And it's the only, is the main project that it has been observed.
So, but what are the limitations? For example, if you want to build up, let's choose a field from the JPass footprint, and then build up deeper observation from the already available observation. Okay. So, what's going to be the problem that you may see?
None, but I don't know, maybe there are none. You just have to observe them more and more times, but no, I don't see any.
The main point here is the timing. Because depending on the fields that are within the JPass footprint, it may have been already observed, maybe observed in 1 year, or maybe in 4 years.
No, it doesn't matter because what we are going to propose is for 5 years.
Okay, in 6 years. Or 6 years. JPass, maybe this field may be observed in 6 years from now. So this is the only point, just to take into account the timing. That information may be available or may not, depending on how far the field is from the
whole point is to see whether these observations, for example, let's suppose that we wanted all the figures, for example. But in the JPass observations, not all the figures will be observed. Because, for example, there are for some reasons, some reasons were more than the others. Okay, if we have a field that can be built on the basis of the already available data, okay, can we in a way influence or request that these fields that are not yet observed to really get observed or not? Right? That's it. That's the whole point.
Yeah, well,
because we would like to take the benefit of the already available observation.
And there is another point here, which is important, which is if the project that you are proposing is making use of JPass data, then it will be considered a JPass paper. So there is some publication policies in JPass that need to be taken into account. So, but this is again, it's something that we can discuss in a case by case. But if you are using JPass data, then it is a JPass paper. There's some rules.
But just if you are a JPass member, because if the data is public.
If you are not a JPass member, you don't have access to this data.
Or
that you are. Many of the.
Or the public JPass data, yes, you are able. The public one.
But if you are a JPass member, the publication policy still applies when the data is public.
Yeah, but if you are not a member, then you can use the public data.
Then it doesn't apply once the data is public. So there's some.
So that's the kind of things that need to be sorted out.
Well, but I guess, for you, for the people that just want to go deeper, and in fact it's much deeper. You are asking, for example, I have seen numbers today, like 25 exposures or 100 exposures. So there is not much different considering the 4 exposure of JPass or not. Okay. So there is no much different. So if you want to go deep to a place where all JPass already have observed, or it will be observed very soon, well, I don't think if the reason is going deep, very deep, as you have presented today and yesterday, I think there is no problem. The problem would be if you want to go, for example, the Virgo cluster, because I'm seeing Luis here. The Virgo cluster, if the Virgo cluster would be in the JPass footprint, then it will be a problem, but it's not. So, and then you can ask JPass strategy at that point.
No, our field also is not in the footprint.
But if it is and you go deep, I think it can be.
To consider that possibility helps, but probably you are right. I mean, it's little advantage.
Yes, it's very small the difference. So
if you are using JPass data, you need to follow. I mean, this is JPass data. That means somehow protected the JPass. So all autos should be. Again, we are covering the casuistics, right? So it depends whether the data is public or is. If the data is not public, then the auto should be in the collaboration. Otherwise, they won't have access to the data itself. This is a critical case. Yeah, there are solutions. It requires a process, other thing that if you think that JPass big field is something now, for those of you that don't belong to the JPass collaboration, please just drop your ears. I'm talking only for the JPass members. If you think that JPass big field would be of high benefit to the JPass collaboration, this is something that this discussion could be triggered within the JPass collaboration. Because at the end, it is up to the JPass collaboration to decide whether they want to go in that direction or not. But this is, I mean, something internal to JPass, but most of you already belong to JPass. So this is something that could be discussed. That's a open track. It is part of the JPass. The JPass big field is performed during JPass time. That means that big field belongs to JPass, and any JPass member will have access to the data and the right to exploit that. No, that means that this proposal wouldn't go to open time, but would be part of the JPass. But again, I'm talking something that is highly speculative, because it depends on the collaboration. So now we are talking about but in open time, you need to go for projects that they are not making use of JPass data. Because if you use totally partially JPass data, then it becomes a JPass.
okay. From my part, I don't have any point to add to the discussion. Okay. For those online, just talk when you feel like you want to talk.
About something which has to do with this.
Or not.
Young one wrote a question in the chat. Perhaps if you want, you can unmute and. Is it, as I mentioned, the planned JPass main survey footprint covers roughly 20% of the ET field. Would it be possible to prioritize observation of this overlapping region before 2028? I am not referring to the entire ET field, as approximately 80% of it lies outside the JPass footprint.
Yeah, well, I have answered. I tried to answer this question that you made in
in your talk. So with the current plan, we are not going to reach that that region. And then what I tried to say is that you can try to convince the JPass collaboration to go to that region with priority, but you have to convince, I guess, the CB, the collaboration board, that Tony here is a representative of this board, I guess, and also I don't know if, Tony, do you understand the question, Tony? Or if not, I can summarize. So
this is not only the collaboration board. I think this is the JPass collaboration as a whole.
Okay.
It's changing the expected growth in the survey strategy.
Yes.
So prioritizing a particular area needs to be very well based on what science this effort is going to produce, and then it will be evaluated with the different science working groups, and at the very end, by or not by the collaboration board, but the discussion starts at a global level within JPass. I think who was the hospital identity? I think it belongs to JPass, right?
Yes. Yuan Huang, yes.
Yeah. So he can raise that point that within his science working group and see how far it goes.
Okay, I think it's to sum up, it's very difficult to change, because different things that it's going to be very difficult, very hard. It's not impossible. In principle, it's allowed to ask for it, but it's going to be very difficult because there are a lot of interest, scientific interest already have been taken into account for the current strategy to observe JPass. So changing it is
it wouldn't be the first time though, that we change the prioritization of the sample in the area group based on scientific opportunities. And to me, this is a very clear scientific opportunity. So they're resonant with that, but this is a discussion that we should start having at JPass. If you consider that an opportunity.
Yeah. So if you want, try it within the JPass collaboration with the current policies, and let's see. If there are no more questions here or online, we should I guess we should end the meeting here. And thank you all of you for coming, for connecting, and we will share at least the presentations made by us. They will be shared probably next week. And I wouldn't share the presentations made by the different teams, the scientific teams, because this is I wouldn't share them. I'm not going to ask the scientific presentations to be shared with them, because it's something that is going to be proposed. So I guess that you can share between you if you feel, but not publicly. But the ones made by Tony, me, Hector Vázquez, also Alessandro, this, if they want, I will share the presentations with you next week, and also I will send the certificates of attendance next week. And that's all.
In my case, also the Aurora presentation, since it may be useful for some people,
okay,
you can share it.
Okay,
no problem.
And the video recording.
And all of the presentations have been recorded in YouTube, and they will be in YouTube, and I will send the links. So thank you to all of you.
Mamen, do you want to say something?
Yeah. I just wanted to ask if we are going to receive any feedback on the letter that we sent.
Yes, you are. When I have time. But yes, a very small, just technical, not scientific, just technical.
Yeah.
Okay.
Thank you.
Yes.
One thing, let's thank Javier for all the work. for you, but this meeting sets a very high bar. And how many meetings have Jamón de Teruel? And you really cannot beat that.
And remember to return this on the table, please.
Sí,